Hello students, good morning all. Welcome to Made Easy GATE 2024 marathon session. This is Sagar Pingili. I am here with computer organization and architecture subject. In this session, I am going to refresh the computer organization concepts along with sample set of the questions. Okay, students, I hope you all are doing good. Okay, so try to refresh all the computer organization concepts in this session and also try to give the correct answers when I am going to display the questions on the screen, right? So I hope that this session will be helpful to you to recap all the concepts of computer organization. All right, my dear students, now I am going to start the session. Are you ready? Very nice. First of all, let me explain the recap or else refreshment of our fundamental concepts of computer organization subject. As you know that in this subject total we have a 3 modules, right, which I explained in the regular class notes. Okay, so module 1 is the data representation, module 2 is the computer architecture, and module 3 is the computer organization. Okay, so first let me start with the data representation. Okay, give me the time to refresh the concepts of data representation. After that we will move on to the sample questions in that area, right? So first let us concentrate on the data representation portion. In the data representation, with respect to the computer system, computer is always understand the data in a form of binary. Okay, so that binary data is represented in the computer by using 2 types of the data formats. That 2 types of the data formats are fixed point data and floating point data. So data formats are basically 2 types: fixed point data formats and floating point data formats. Right. So when we see the fixed point data formats, here fixed point data is represented with 2 formats, that is unsigned data format and second is signed data format. Unsigned data means only the positive data. Signed data means both positive and negative data. Okay, so in the unsigned data representation, to represent positive data, unsigned format is used. Then in the signed data representation, to represent positive and negative data, there are 3 formats present. First one is the sign magnitude format, and one's complement format and 2's complement format. Okay, right. Fixed point data basically 2 types, unsigned and signed data. Unsigned data means only positive data, that is represented with a unsigned format, and signed data means both positive and negative data, that is represented with sign magnitude format, one's complement format and also 2's complement format. Very good, right. Then come to the unsigned format. Unsigned format range is 0 to 2 power n minus 1. You know that. This is the n bit CPU. N bit CPU stands for word length of the computer is n bit. Then come to the Sign magnitude data. Sign magnitude data range is minus 2 power n minus 1 minus 1 2 plus 2 power n minus 1 minus 1. This is the range of a sign magnitude data. And come to the ones complement data. Ones complement data range is same as sign magnitude data range. Okay. So this is the ones complement data range. Then 2's complement data range minus 2 power n minus 1 2 plus 2 power n minus 1 minus 1. Okay. So this is the range of a unsigned data and signed data with respect to n-bit CPU. Correct? Next. When we see the arithmetic operations, there are different arithmetic operations takes place on unsigned numbers as well as the signed numbers. That is addition, subtraction, multiplication and division. These are the primitive arithmetic operations takes place on the respective data. Okay. So after performing the arithmetic operations, there may be a possibility of range exceeding conditions. Okay. So when we see the arithmetic operations here, both the cases, that means unsigned numbers as well as the signed numbers, if you take addition operation, n bit plus n bit, when we are performing the addition operation between the two n bit numbers, result will be expressed with n plus 1 bit size. Okay. When we are performing the multiplication between the two n bit numbers, n bit into n bit, then result will be expressed with 2 n bit size. Okay. Then when we take the division operation, okay, if the divisor is n bit, dividend must be expressed with 2 n bit. These are the arithmetic operations related points. Addition operation point of view, result length is n plus 1 bit. Multiplication point of view, result length is 2 n bit. And division point of view, n bit divisor if we use, dividend must be expressed with 2 n bit. Okay, right. So when we see the computer, word length will be varies, depends on the CPU used in the system. Suppose 8-bit CPU, word length is 8-bit, 16-bit CPU, word length is 16-bit, 32-bit CPU, word length is 32-bit. Similarly, if you take generalization, n-bit CPU, word length is n-bit. Okay, so in the n-bit CPU, all the registers are having the size of n-bit to hold the data. So all the data registers size is equal to the word length of a CPU. All registers are not a data registers. Some of the registers are used to hold the address information also. So that's what which I already explained in the regular class notes. Program counter register holds the instruction address which is present in the memory. Therefore, program counter size is equal to main memory address size. Okay. Similarly, accumulator register is there. Accumulator register is used to hold the data. So that accumulator register size equal to word length of a CPU. So finally, what I am going to conclude is all the data registers size equal to the word length of a CPU, and some of the registers are designed with a special purpose, so that those registers size depends on the respective purpose. Clear? Alright. Now come to this. When you see the n bit plus n bit, that is the addition operation, here n plus 1 bit is the result. Okay. So if this is a unsigned number, this 1 bit range exceeding condition, unsigned data range exceeding condition is represented with a condition, is represented with a carry flag. So carry flag is used to represent the range exceeding condition of a unsigned number. So carry flag condition is there an extra bit out of MSB? That is the condition. Similarly, if you see the signed numbers, in the signed data, range exceeding condition is represented with a overflow flag. overflow flag. You know the condition of the overflow? Condition of the overflow flag is there is a carry into the MSB and no carry out of the MSB or vice versa. Okay. If we are not going to represent condition with a plain text, we have a alternate condition that is called as the XOR operation between in carry and out carry with respect to MSB is a overflow condition. Okay. Right. We have one more alternative method to represent the overflow condition, that is when the same sign data is processed, result contain opposite sign, then overflow present. So that overflow condition will be described in 3 different formats. Okay. So when carry flag is set, by default we are taking extra bit in the MSB when the data is unsigned numbers. Okay. When overflow flag is set, we cannot take extra bit as 1. Simply when overflow flag is set, we are going to bring the carry flag status into the MSB position of a final result. Okay. To justify the final output. This point I already explained in detail in our regular class notes. This is just a refreshment session. Therefore, just recap the concepts, okay, which you already learn in the regular session. Clear? All right. Now, come to the another point of the unsigned numbers. For the unsigned numbers, zeros padding is required. Unsigned data requires the zeros padding. That means when you are storing the small data into the large storage space, there is a need of the extra bits information. Okay. So data size is small, storage space is large. To store small data in the large space, zeros padding is used. When it is a signed data, to store the small signed data in a large storage space, we use the sign extension process. Sign extension is nothing but replication of MSB. MSB replication is called as the sign extension. Sign extension process used in the signed data storage, and zeros padding is used in the unsigned data storage. Is it okay? Alright. Now come to the multiplication. When you see the multiplication, this is n bit into n bit is equal to 2n bit. To store the final product, register pairing is used. Register pair is used to store the result, because every CPU having the n bit data register, when the result is 2n bit, compulsory 2 registers are paired to hold the final product. So in this case, unsigned multiplication is controlled by the multiplier bits. When the multiplier bit is 1, partial product is multiplicand, multiplier bit is 0, partial product is 0. So that partial products are generated based on the status of the multiplier. After generation of the partial products, provide the summation to produce the final product. So that is the way to perform the multiplication between the unsigned numbers. When you take the signed numbers, there we use the Booth's algorithm. Booth's algorithm is also named as the bit pair algorithm. So in the bit pair algorithm, bit pairs are formed based on the multiplier to control the multiplication. Okay, in that bit pair formation, to get the initial bit pair, one assumption is required, that is q subscript minus 1 is initialized to 0. Okay, so based on the bit pair, different actions are performed in the multiplication. When the bit pair is 0 0, only arithmetic shift right operation takes place in the multiplication. When the bit pair is 0 1, addition operation along with arithmetic shift right operation takes place in the multiplication. When the bit pair is 1 0, subtraction operation along with the arithmetic shift right operation takes place in the multiplication. Okay, when the bit pair is 1 1, only arithmetic shift right operation is performed. Okay, 0 0 1 1 bit pair is associated with arithmetic shift right operation. 0 1 bit pair is associated with addition and arithmetic shift right operation, and 10 bit pair is associated with subtraction and arithmetic shift right operation. So by using these operations, multiplication process is controlled in the signed multiplication. Okay, that is the 2's complement multiplication. Okay, by default signed data is a 2's complement data. As you know that sign magnitude concept is practically not present. Reason is 0 contain the two different codes, that is data redundancy, duplication of the data redundancy to represent 0. That's what sign magnitude concept, 1's complement concept, both are practically not present. So by default signed data is a 2's complement data. Okay, right. So once you know this information, with this you may answer different set of the questions which are associated with a fixed point data format. If you see the PYQs, in the PYQs there are different questions formulated based on the range of a signed number, okay, based on the range of a unsigned number, and also based on the sign extension, and also based on the multiplication process. So with this refreshment, okay, you may recollect the information from the your memory system, okay, which you already stored when you learn the regular classroom session. Okay, now come to the floating point data. Right, when you see the floating point data representation, in the floating point data, we have a separate structure actually. That data structure is plus or minus m into b power plus or minus e. This is the floating point data structure. Okay, so plus or minus indicates the sign of a data, m indicates the mantissa, that is a fraction part of the data, b indicates the base of a data, e indicates the exponent of a data. Is it okay? So plus or minus m into b power plus or minus e, this is the data structure. So in this floating point data, when you want to store the data, compulsory we are using the normalization. Normalization structure is 1 point BBB into 2 to the power of plus or minus e. That means before the decimal point digit is always 1. Okay, after that in the fraction you may have 0 or 1. This is the normalization. Okay, when the data is in the normal format, that data will be stored into a memory. That data will be stored into a memory by using the IEEE formats. Without normalization, if you store the data, there may be a loss of data. Already you know that. That's what, before storing the data into the memory, compulsory we need to convert data into a normalization format. Once data is in the normal format, that will be stored into a memory. At the time of storing the data, there is a need of the format. Okay, so that formats are given by the IEEE. So here IEEE provided two types of the formats. One is the 32-bit format. Second is the 64-bit format. Two types of formats given by IEEE. When you see the 32-bit format, here sign, biased exponent and mantissa, 3 fields present, 1 bit allocated for sign, 8 bits allocated for BE and 23 bits allocated for mantissa. This is the layout of a 32-bit format. Similarly, if you see the 64-bit format, still we have the same structure, sign, BE, mantissa. 1 bit is allocated for sign, 11 bits are allocated for BE and 52 bits are allocated for mantissa. Okay, so this is the IEEE format. Very nice. And next one, in the IEEE formats, when you want to store the data, there is a need of the biased exponent. So here bias value is represented in two ways. First is the normal bias, second is the excess bias. Okay, so normal bias is nothing but a plus 2 power n minus 1 minus 1, that is maximum possible positive exponent is called as the bias. This is the normal bias. Okay, what is n? N indicates the number of bits in the BE field. Number of bits in the BE field is the n value. Excess bias, center of the exponent range, that is center of the exponent range 2 power n by 2, or else this is represented as 2 power n minus 1, right? This is called as the excess bias. So there are two types of biasing present in the formats. Okay, default bias in the IEEE is the normal bias. Okay, so once you know the bias concept and format, you may store data into the memory, and also you may read data from the memory. So storing always requires the step-by-step procedure, but reading of the data have the some optimistic method. So when you are reading the data from the memory, optimistic method is minus 1 to the power of s into 1.m into 2 to the power of BE minus bias. So by using this, you can able to retrieve the data from the memory. Okay, so after completion of this, when you want to represent the range of a floating point data, their sign is positive or negative, here there is no problem. And exponent range, this is depends on the bias. Suppose when we use the normal bias, then range of the exponent is minus bias 2 plus bias plus 1. This is the exponent range. When we use the excess bias, then exponent range is minus bias plus 1 to minus bias 2 plus bias minus 1. Yes, this is the normal bias and excess bias formula. Okay, right. Then come to the fraction, that is mantissa range. Mantissa is also called as the fraction. So here mantissa range is generalization. Minimum 1 to 2 minus 2 to the power of minus mantissa size. This is the generalized representation of the exponent range, mantissa range and sign range. Okay, all right. So finally, when you want to take the range of data, okay, that is like this, plus or minus 1 into 2 to the power of minus bias 2 plus or minus 2 minus 2 to the power of minus mantissa size, okay, into 2 power plus bias, positive bias. Okay, so this is the generalized range. I just given the generalized range, okay, based on the IEEE formats. If you take the 32-bit format and if you take the 64-bit format, these values are varies. Okay, but when exam is concerned, there are the hypothetical formats present. So with respect to hypothetical formats, the corresponding range is varies. So you try to remember these generalization formulas. When you remember these generalization formulas, these are applicable and also suitable to every hypothetical format which is given in the question paper and also IEEE formats. Okay, all right. Next, come to the special values. Actually, when we see the floating point data, in the floating point data, we don't have a zero value, we don't have a infinity value. Okay, but we want 0 and we want infinity. For what purpose? To handle the out of range conditions. So to represent 0, to represent infinity, there is a need of the special exponents. Okay, so that means special values are defined with the help of special exponents. For that purpose, minimum exponent and maximum exponent both are reserved for the special values. Okay, so here if you take special values, there is a special value 0, okay, and there is a special value, okay, plus or minus infinity. Then also we have a special value NaN. Then what is the code for the special value 0? Sin, Be and mantissa. Special value 0 means sign is positive or negative, Be all zeros, mantissa all zeros. Okay, this is the code for the special value 0. Next, what is the code for the special value plus or minus infinity? Sin 0 or 1, biased exponent all ones and mantissa all zeros. Okay, this is the binary code which is reserved to represent the special value plus or minus infinity. Then come to NaN, not a number. Not a number is nothing but a error. So sign is 0 or 1. Okay, biased exponent is all ones and mantissa is not equal to 0. Okay, so all zeros mantissa is used for the special value infinite. So excluding all zeros mantissa, remaining mantissas are used for the NaN. So these are the codes, right? At the same time, when we take the all zeros Be, this is the minimum Be, first mantissa is used for the special value 0. After that we have some other fractions. Those all fractions are also having the special exponent, but those fractions are not named as the special value 0. Okay, those fractions are named as the subnormal numbers. So subnormal numbers, subnormal data. Code is what? Sign is 0 or 1, right? Biased exponent is all zeros, correct? Then mantissa is not equal to 0. Okay, so here two exponents are covered, minimum exponent and maximum exponent, both are covered to represent the special values along with the subnormal numbers. Okay, after excluding the special exponents, rest of the exponents are called as the representable exponents. Okay, so here representable exponents are like this: all zeros in Be less than, okay, Be less than all ones in Be. Okay, so this is the generalization actually. Minimum exponent, maximum exponent. Between minimum to maximum exponents, how many exponents are present? Those all are called as the representable data exponents. So representable data is a special name actually. User point of view, representable data is nothing but minimum to maximum. But IEEE point of view, representable data means the data which is having the representable exponents. Representable exponents are present after excluding the special exponents. Okay, all right. So this is the representable data. In the representable data, minimum representable data and maximum representable data. For example, minimum representable data, if you take minimum representable data, if you consider, okay, with Be field size of suppose 4 bit, suppose they have a Be field size of 4 bit, then what is the minimum representable data? Sign may be positive or negative. Be minimum representable data 0 0 0 1 and mantissa, minimum means ascending order, so low to high, minimum fraction, that is all zeros. This is the minimum representable data where the Be field size is 4 bit. Similarly, maximum representable data, maximum representable data. Okay, with BE field size is 4 bit. What is that? Sign is 0 or 1. Okay, BE maximum representable exponent is 1110. Don't take all ones. All ones BE, special BE. All zeros BE, special BE. So representable BE means BE after excluding the special exponents, right? Then mantissa, largest, maximum, so descending order, all ones. Like this we are going to represent the minimum and maximum representable data values. Okay, so finally when you see the floating point data, in the floating point data we have a total 5 types of the elements. First one, special value 0. Okay, then second one, subnormal number, subnormal data. Next one, special value plus or minus infinite. Next one, NaN, that is nothing but error. Next one, representable data. Okay, so in the floating point data representation, 5 types of data entities are present, 5 types of data elements are present. Okay, fine. So after performing the arithmetic operations, as you know, addition, subtraction, multiplication, division, these are the arithmetic operations. After performing the arithmetic operations, there is no guarantee that result is always present in the range. So that's what compulsory we want the some special cases to handle the out of range data. Okay, to handle out of range data in the floating point data representation, we have a rounding mechanisms. Okay, so underflow data, okay, the data which is very small, underflow data is represented with the round to 0 technique. Positive side overflow data is represented with the round to plus infinity technique. Okay, negative side overflow data is represented with the round to minus infinity technique. Okay, these are the out of range data. Out of range data elements are represented with the rounding techniques. Okay, so these rounding techniques are used to represent the out of range data. Is it clear? And round to nearest, round to nearest means whatever the representable data is there, that will be reported with respect to given binary code. Okay, so this is the information which I want to give the refreshment in the data representation topic. Students, as you know that computer organization and architecture subject is a conceptual subject. Okay, theory based subject. Okay, when it is a theory based subject, first of all you should know the fundamental concepts. Once you know the concepts, then you are in a position to understand the question. When you know the question, directly you can answer the question. So without knowing the terminology, without knowing the question logic, you never there in a position to answer the question. Okay, so COA questions are static questions because computer is a real machine, that is a static machine. Designing is also static, terminology is static. Okay, so any question you can see, okay, we have the same terms, there may be a small changes in the logic. So when all terms are same, all the structures are same, okay, if you know the basic concepts, then compulsory you are in a position to answer all the kinds of questions present in the paper from the computer organization subject. Okay, so then arithmetic operations, anyway you know arithmetic operations are addition, subtraction, multiplication, division. In the addition and subtraction point of view, only we are going to make the both the numbers exponents equal. If they are not equal, take the difference between the exponents, align the smaller exponent mantissa to right direction up to the difference. Then keep that exponent as a common, do the addition or subtraction operation between the mantissas, normalize the result, store the result into memory. That is for addition and subtraction. When you see the multiplication, first add the exponents, later multiply the mantissa, normalize the result, store the result into memory. When you see the division operation, first you need to subtract the divisor exponent from dividend exponent. After that, divide the mantissas, normalize the result, store the result into memory. Okay, so this is the information which I want to explain as a detailed refreshment in the topic of data representation. I hope you understand the same. Now I am going to show the sample questions. All of you see the sample questions and solve the question and give the answer immediately. Yeah, take this question. Consider the following hypothetical format. This is the hypothetical format given. Sign is 1 bit, B is 6 bit, mantissa 9 bit. Final product in the memory in hexadecimal after perform the multiplication between the following data. This is the data given. Okay, do the multiplication and store the result into memory. At the time of storing result into memory, use the respective format and report the final result in a hexadecimal format. Okay, please give the answer. Yeah, what is the answer? Do it fast. Completed? Yeah, I want to see your answer. Right, see this. Here two elements given, x and y. X equal to 4.25, this is decimal value, and y is the 3.5, this is also decimal value, base 10. Then we are going to perform the multiplication, x into y, that is equal to 4.25 into 3.5. Okay, what is the output? 14.875. This is the output, correct? Now this 14.875 binary equivalent is 14, 1110, 0.875, 111. Okay, convert the decimal value into binary. Okay, all right. Now is this data present in the normal format? No, we need to check the normalization, 1.BBB. It is not in the normal format, so that align the data to right direction 3 times. So 1.110, 111 into 2 to the power of plus 3. So this is the normal data format. Normal data format means 1.BBB. When the data is not in the normal format, apply the mantissa alignment process, convert the data into normal format. Yes, this is the normalized data. This normalized data is stored into the above format. Okay, so what the format given? Format given is sign, biased exponent and mantissa. Okay, sign is 1 bit, biased exponent given 6 bit, right? Mantissa given 9 bit. Is it okay? This is the format mentioned in the question, 1 bit, 6 bit, 9 bit. Alright, then what is the bias? Bias information not given. Default bias is normal bias. So normal bias plus 2 power n minus 1 minus 1. That is plus 2 power 6 minus 1 minus 1. This is plus 31. Is it okay? Alright. Now store the result. First, sign of the data is positive. So 0. Second, BE is equal to AE, actual exponent plus bias. Correct? Actual exponent is 3. AE is equal to 3. 0, 0, 0, 0, 1, 1. Then bias. Bias is 31. So 0, all ones. Right? Adding them. Like this. This is the biased exponent. Right? Then Mantissa. Third one is Mantissa. Mantissa is already present in the normalized format 1.110.111. Yes, this is the Mantissa. Now store this information in the above format. Okay. So when we store this in the above format, sign is positive 0, BE 100, 010, then Mantissa only fraction 110, 111, remaining 3 bits are padding with zeros. Okay, this is the storage. Question is expecting hexadecimal value. Group 4 bits like this. Okay, what is this? 4, this is 5, this is B, this is 8. 4, 5, B, 8. Base 16. Yes, this is the question. In the question, when you see the option, okay, right option is C. 4, 5, B, 8, base H. Okay, simply we did the multiplication. After multiplication, result is converted into a normalized format. That normalized result stored into a memory by using the given hypothetical floating point structure. Okay, after storing, grouping 4 bits to represent the hexadecimal value. So right answer is C. Let me see how many of you given the right answer. Meanwhile, I am going to display the solution also. Please communicate in the chat so that I can able to see your answer. Yes, Arya, DGS, Rajat, yes. My dear students, thank you so much all. Thank you so much, my dear students. You all are given the right answers. I am feeling very happy. Okay. Reason is, when the students are giving the right answer, okay, after understand the concepts of regular class notes, suddenly when you given the right answer, every faculty feeling very happy. Okay. So you are making my hardware happy today. Thank you so much. Maintain the same positive energy till end of the session, because in this session you may get some different questions which are different from your regular class notes. Okay, all right, fine. Okay, very good. Now see the next question. Here I don't want to waste your time. Okay, simply I am giving the refreshment of the concept. Immediately I am giving you the sample questions for the practice. Okay, in the yesterday's class, actually in the yesterday I uploaded the GTQ, okay, gate through questions. In that GTQ session also I explained a set of questions, expected questions with different logics. So you please try to watch that session also to get more questions. When you do the more questions, okay, you may perfect with logic. Once you know all the logics, okay, at the end of your final paper, your all answers are correct. Okay, all right. This is the question. Please read the question, give the answer. Consider the following format. This is the format excess bias. Which of the following represent NAN? NAN, not a number. Teja, Pratik Sagar, thank you dear students. Pratik Sagar, thank you so much. Which of the following represents the NAN, not a number? So here options contain the hexadecimal format. When options contain hexadecimal, so convert that hexadecimal into binary and report the value. So you know the NAN code. NAN code is sign, BE and mantissa. Sign is 0 or 1, BE all ones, mantissa not equal to 0. So this is the NAN binary code. Is it okay? This is the NAN binary code. Now here option A 7 0 1 1 1, E 1 1 1 0. Okay, all zeros 0 0 0 0 0 0 0 0. Right. So if you see this, divide accordingly the format 1 bit 7 bit 1 2 3 4 5 6 7, 1 bit 7 bit and mantissa S B E M. So here they give an excess bias. Even it is excess bias or normal bias, NAN code is same. NAN code is not changed when bias is changed. Okay, normal bias, excess bias. In both of the cases, NAN binary code is same. Okay, so here, is this code matching to that? No. So this is not correct answer. B 7E not matching. Then 7F20. See B 7 0 1 1 1, F 1 1 1 1, 2 0 0 1 0 0 0 0 0 0. Divide this into the above format. 1 bit, next 7 bit and remaining bits are mantissa. Now is it matching to above format? Yes, this is matching. This is NAN. Now come to C. 7F00, 7 0 1 1 1, F 1 1 1 1, then 0 4 0 and 0 4 zeros. Now interpret this into the above format. Okay, interpreted. Fine. This is sign, this is biased exponent, this is mantissa. Compare with the code. Is it matching? Not matching. Okay. Sign is 0, BE all ones, mantissa all zeros. So this is not a NAN. This is not a NAN. Okay. Now come to the option D. Option D. What is given here? F 1 1 1 1, F 1 1 1 1, 4 0 1 0 0, 0 0 0 0 0. Okay. So this is the code. Interpreting into format sign, BE and mantissa. Okay. Now compare this code with the NAN code. Is this code matching with NAN? Yes, this is matching. Okay. So in this question, right answer is B and D. B and D. This is the right answer. Let me see how many of you given right answer. NAN, not a number. B and D is the right answer. Thank you so much, my dear student. Again, Rajat Bharati, Siddhi, Shinde, Akshay. Yeah. So all students given the right answer. Everyone, whoever responded in the chat room, okay, all are given the right answers. Okay, thank you so much. Okay, maintain the same energy in your final paper also. Okay, because Concepts are static concept. Again, I am going to giving the important point. Static concepts. When you know the concepts, you can easily answer all the questions. Okay. Try to minimize your stress levels and tension level. Okay. When you are in the exam hall. Okay. When you are sitting in front of the final examination paper. Okay. Don't bring all the non-functional requirements into your brain. Okay, non-functional requirements means your tension, your overthinking, your stress level, these all are the non-functional requirements. When they are dominated, automatically your functional requirements are diluted. Okay, that's what, try to manage these non-functional requirements. Don't bring them into your memory system when you are giving the final paper. Okay, all right. Next, please. This is my handwritten question. Please take this question and give the answer. Nowadays, actually, questions are very lengthy questions nowadays because of MSQ, multiple selection question. There is a chance of there are multiple options which are correct or multiple options which are false. So you need to verify all the options carefully. That's what questions consumes the time. Okay, you literally questions consumes the time, but in the exam you need to minimize that time. How can you minimize that time? When you practice the concepts, when you practice set of questions. Okay, at the end the overall analysis time will be minimized. Okay, this is the question. Please read the question. Consider the following format. This is the format given. Which of the following statements are true? Which of the following statements are true? Yes, these are the statements given. This is MSQ question. Some students are asking that, sir, please mention whether it is MSQ or MCQ. This is MSQ question. Previous one also MSQ question. So actually this is just brainstorming session only, correct? Okay, so when it is a brainstorming session, you need to analyze all the options. Don't separate it MCQ, MSQ. Okay, in the final paper that is different story, but here verify all the options, then give the answers. Which of the following statement is are true? What is the first option given? This is the first option. Minus 15 to plus 16, range of exponents are possible in the system. So when I see the first statement, this first statement is belongs to exponents range. So exponents range depends on the BE field. Now go to the format and take the exponent range. Okay, with respect to the format, BE field size is 5 bit. When BE field size is 5 bit, what is the meaning? Normal bias equal to plus 2 power 5 minus 1 minus 1. This is plus 15. Okay. So normal bias, exponent range, direct formula you know, that is minus bias to plus bias plus 1. This is the formula what you have. So this is minus 15 to plus 16. Is it okay? This is the range, exponent range. In this format, they are not given anything about the bias. When they are not mentioned anything about the bias, default bias is normal bias. Okay, normal bias value plus 15. range of exponents are minus 15 to plus 16. Okay, now this statement, minus 15 to plus 16 range of exponents possible. Yes, this statement is true. True statement. Now come to the second one, this one. Exponent minus 16 is a legal exponent when format is uses excess bias. Now see this. Second statement, when format uses excess bias. See, excess bias. What is excess bias? That is 2 power 5 minus 1. This is equal to 16. Excess bias is 16. Excess bias exponent range is what? Minus bias 2 plus bias minus 1. Is it okay? This is the range. That is minus 16 to plus 15. This is the excess bias exponent range. In the excess bias exponent range, minus 16 is present or not present? Yes, present. So minus 16 is a legal exponent in the excess bias exponent range. Okay, so this statement is also true. Minus 16 is a legal exponent in excess bias. Minus 16 is a illegal exponent in the normal bias. Clear na? Alright. Next please. Pratik Sagar, tell me, third statement. Pratik, what about third statement? Is this third statement true or false? See, this is the value given. Sin plus or minus 1.101101 into 2 power plus 18. Plus 18 is a special value plus or minus infinity. Is this statement true? Is it plus or minus infinity? Plus or minus infinity binary code is what? Sin BE M. Sin is 0 or 1. BE all ones. Mantissa all zeros. Yes, this is the binary code for special value plus or minus infinity. Okay, but here what is given? They are given illegal exponent. Illegal exponent. Actually, this is out of range data. This out of range data is not a special value infinity. That out of range data is reported as a round to plus infinity. That is round to plus infinity or round to minus infinity. This is not a special value. Special value binary code is that. So this is not matching to special value binary code. This is actually out of range data. Out of range data is reported with the round to plus or minus infinity technique. Okay. So actually, what about this? This value is the round to plus or minus infinite. Yes, this is round to plus or minus infinite. But what they given? This is a special value plus or minus infinite. That's what this statement is false. False statement. Very good. Then come to option D. For BC base H, decimal equivalent is 15.5. What about this answer? Is this statement true or false? Yeah, you are correct, Pratik Sagar. Thank you so much. So many students, you already given the answers. When I see the chart room, okay, chart section, in that section already you are with answer. Thank you so much. That kind of accuracy required, dear students, that we want. Finally, 4 BC 0 1 0 0, B 1 0 1 1, C 1 1 0 0. Put this information in the above format. Sin, next BE. How many bits? 5 bits BE. That is given like this. Okay, sin BE and M. Value please, minus 1 to the power of 0, 1.1111 0 0 into 2 to the power of, what is this? B 1, this is 2, 4, 8, 16, that is 18. 18 minus 15. So this is plus 1.111100 into 2 to the power of 3. So this value is 1111.1. That's it. Into 2 power 3 minus 3, exponent cancel. So this value is plus 15.5. Yes. Is this matching or not? Yes, matching. 4 BC decimal equivalent is 15.5. So D is right answer, true statement. So which of the following statements are true? So right answer is what? A comma B comma D. This is the right answer. Okay, all right. This is the question. So right answer is A, B, D. Rajat Bharti, thank you so much. Yeah. Oh my God. Students, you all are correct. Right. Thank you all. Okay, like this, you please practice the questions which are related to the data representation. So here I am not concentrating on the range of data. Generally fixed point data range, I given the formulas. Okay, so according to the question, when they given any fixed number, 9-bit, 8-bit, 10-bit, 12-bit, okay, apply that given number in the generalized formula that gives you the range of respective data. And floating point data formats, you know how to store the data, you know how to read the data, you know range of data. So all the concepts which I explained in the regular class and also in the refreshment session, okay, everything is matched, your all answers are correct. Okay, according to my interpretation, what I feel is, okay, every student is very happy when the questions are actually mathematical type. So when the question is a mathematical type question, then every student is in a position to answer the question correctly. Okay, but actually students are taking the wrong interpretation when the question is having the conceptual information. Okay, so according to my opinion, data representation point of view, if any question is in the paper, every student is in a position to answer that question, damn sure. Okay, every student is in a position to answer data representation related question, because data representation is very much close to generalized mathematics. Okay, so in that module you have the 100% confidence, there is no problem at all. But here problem is starts from the conceptual question, that is from the module 2 onwards terminology creates confusion. Okay, so let me start computer architecture module. Okay, let me give the refreshment of those concepts. After that I will explain set of questions, not only one or two. We will see more questions in the computer architecture concept where students are taking more mistakes. Students are doing more mistakes actually. Students are taking misinterpretation. Okay, where students are taking misinterpretation or where students are doing more mistakes, those questions we will see in the computer architecture. Okay, so let me start the computer architecture module. Let me give the refreshment of that module concept. Later we'll move on to questions. Okay, Bharati? Pratik, Sagar, you all are accepted, na? Okay, fine. Right. Now, let me take the refreshment of computer architecture. I am just writing the points quickly because these points already, you know, these points already present in your running notes and also present in your short notes. Okay, no need to write any points, just listen the refreshment points which I am going to deliver now. Fine. Okay. Now first thing, in the computer architecture, as we know that our computer system is a one human system. According to one human system, okay, application program is always required in the main memory to execute. So main memory size is always restricted by the CPU. In the CPU, how many address pins are present, based on that main memory capacity is restricted. Okay, so we cannot increase the main memory size according to our choice. So how much main memory possible in the computer, that is restricted by the microprocessor address pins. Okay, that's what 8085 computer supports 64 KB RAM, because 8085 microprocessor contains 16 address pins. Okay, 8086 microprocessor supports 1 MB RAM, because 8086 microprocessor contain 20 address pins. So how much main memory possible in the computer, that is restricted by the number of address pins in the CPU. Alright. So main memory address is called as the physical address. So CPU always generates the physical address. CPU always generates the physical address to execute the program, because our subject is a computer organization subject. You know that. According to computer organization subject, imagination is program is in the main memory. Main memory address is a physical address. So CPU generates the physical address to execute the program. That is fixed. Next point, memory. When you see the memory chip organized into cells. Cells are addressable units. Default cell size is byte. So that memory is a byte addressable memory. Okay, memory chip recognizes the control signals, read signal and write signal. Okay, so to access any information from the memory, there is a need of the memory request. That request contain address with control signal. Okay, address enables the cell. By using control signal, we can access the information from the memory. Very good. So finally, when you see the memory cell size is by default byte. Okay, memory storage structure is default little endian storage structure. Okay, memory cell by default contain address, memory cell by default contain control signals. Is it clear now? This is about memory. Then come to the CPU. Okay, when we see the CPU operations always performed on a word formatted data. So 8-bit CPU, word length is 8-bit, 16-bit CPU, word length is 16-bit, 32-bit CPU, word length is 32-bit, and so on. So data type of the CPU is word. So CPU always accessing data from the memory in a form of words. Okay, so to synchronize the CPU data type with a memory data type, there is a need of interfacing. That interfacing is implemented during the design time of a computer. At the time of designing the computer, designer specifies the interfacing. Okay, 8-bit CPU, 1 cell interfacing, 16-bit CPU, 2 cells interfacing, 32-bit CPU, 4 cells interfacing. Like that, interfacing will be adjusted according to the word length of a CPU. That is the responsibility of the designer during the design time of a computer. Okay, so here CPU data type is word. Okay, so this word length is varies between the CPU and between the CPU to CPU. So here what is required? According to the CPU, there is a respect to interfacing adjusted like this. CPU memory. Here CPU data type is word, memory data type is byte. You know that. So here what happens is, suppose it is 8-bit CPU. Then 1 cell interface required. Okay, suppose it is a 16-bit CPU. Carefully listen. Here 2 cells interfacing required. Suppose it is a 32-bit CPU, then it is 4 cells interfacing required, like that. So between the CPU and memory, interfacing will be adjusted. Okay, when interfacing is adjusted, what happens, you know, these cells are accessed in parallel. These cells are accessed in parallel. That means what? When CPU send the memory request, when CPU send the memory request, okay, like this, at a time multiple cells are accessed in parallel, then it will give one word data. That means what? One memory request, one word data is accessed. One memory request, one word data is accessed. In that memory request, multiple cells are accessed in parallel. When multiple cells accessed in parallel, no need to count them physically. Okay, so what we need to count? Number of references. If I want to access 100 words, 100 memory references required. If I want to access 200 words, then 200 memory references required. Like that, we are concentrating only on the number of memory references based on the number of words required to access. Okay, how many words are required for the CPU? Those many times memory references are generated by the CPU. Okay, so this interfacing need not to consider, because any number of cells you may interface, they all are accessed in parallel. So this is need not be required. So our requirement is how many words of data accessed from the memory. How many words? 8 words, then 8 references generated by CPU. 20 words, then 20 memory references generated by CPU. Like that, CPU always accessing the data from the memory in a form of words. Very nice. Okay, to provide the interfacing between the CPU and memory, there is a system bus present. System bus is used between the CPU and memory. So this system bus having the address lines and data lines and control lines, you know that. So by using these 3 category of the lines, communication takes place between the CPU, memory and also IO. So major components of a computer communicated each other with the system bus. Okay, so here system bus configurations are 3 types actually. Bus configurations 3 types. 3 types of bus configurations: IOP, input output processor, isolated IO, okay, that is IO mapped IO, then memory mapped IO. Like this, we have a 3 types of the bus configurations. Okay, why we use bus configurations? We use bus configuration to avoid the conflicts. To avoid the communication conflicts, bus configurations are used. Under which case conflicts are present? When there is a common bus, common control signals, common address space used between the memory and IO, there is a possibility of conflict. That's what we use the configuration. Already you know this information. Okay, once the bus is ready, CPU is ready, memory is ready, we are executing the instruction. Okay, at the time of executing the instruction, the total execution sequence is described with a instruction cycle. Instruction cycle is used to describe the execution sequence of a program. This instruction cycle contains 2 subcycles, as you know, fetch cycle and execution cycle. Okay, students, it is a refreshment session. Okay, don't think about speed. Okay, those who are listen the concepts first time, they may feel that, sir, you are going to explain the concepts in a super express speed. Okay, it's not like that. This is refreshment session. This session is helpful to the GATE aspirants who are going to give the GATE paper 2024. Okay, so first time learners, you may feel that this class is running very fast. Okay, but this is required for the GATE 2024 students, okay, to recap all the concepts. So that's what, don't create any bad opinion about the speed. Okay, so I know that first time learners always feel that, hey, sir is explain the concepts like anything according to sir's speed, we are not getting any information. That may be the opinion from the first time learners. Okay, this session is for the GATE 2024 students. Okay, so they already have the enough information related to this subject. That's what I am going to explain the concepts with a refreshment, a bit speed. Okay, try to understand. Right, next, this is the instruction cycle, fetch cycle and execution cycle. Now come to the fetch cycle. When you see the fetch cycle, what happened is, in the fetch cycle, instruction fetch will be happens. Instruction fetch means read the instructions from the memory based on the program counter. Okay, simply instructions are fetched. Yeah, instruction fetch means fetch the instructions from the memory based on the PC. Execution cycle matlab process the instruction. Right, process the instruction, execute the instruction. That means fetch one instruction from memory, execute that instruction. After that, fetch second instruction from memory, execute second instruction. After that, fetch third instruction from memory, execute third instruction. It will be continuously happening. Okay, so end of the program is represented with the halt. By using the halt statement, the total program execution will be suspended. What is halt? Halt is a unconditional jump with starting address is target address. This is the halt. So program ending is specified with a halt statement. Because of end of the program is halt, instruction cycle does not have the physical ending. So this is infinite loop. This is infinite loop. Okay, when infinite loop is there, how we know that program execution is completed? We know that with the help of halt instruction. Clear? Very nice. Now come to the states. When you see instruction cycle, fetch cycle contain IF, instruction fetch. Execution cycle contain ID, OF, PD, WB. These are the different states present in the execution cycle. Okay, so in the IF, compulsory 1 MR required. This is mandatory. Okay, to fetch the opcode, that is first word of the instruction. Remember this. First word of the instruction is fetched. First word of instruction compulsory contain, first word compulsory contain opcode. So opcode is fetched from the memory. Okay, first fetch cycle means 1 MR compulsory required. Okay, to fetch the first word. The first word of instruction contain opcode. That opcode is connected to ID. See this. In ID, okay, what will happen? Multiple memory references required. Multiple memory references required to fetch the remaining part of instruction. Suppose instruction size is 2 words, instruction size 3 words, instruction size 4 words. Okay, so the remaining part of instruction fetched. Okay, for that purpose, multiple memory references are required to fetch the complete instruction after decoding the opcode. Is it okay? After decoding the opcode. Next, operand fetch. Listen, this operand fetch and WB, these two, operand fetch and WB, these two states are required for the data access. When the question contain number of memory references required to access data, then you need to count operand fetch memory references, WB memory references. That's it. So here data access, that is memory references, depends on addressing modes. Okay, based on the type of addressing mode used in the source location, type of addressing mode used in the destination location, number of memory references are varies. Okay, data access memory references varies. Okay, then PD. PD means only processing, that means ALU operations performed. PD means only ALU operations performed. Like this, when you are talking about the instruction accessing counts the IF memory references, ID memory references. Instruction accessing means these two memory references you need to count. Data accessing means operand fetch and WB memory references you need to count. Okay, only instruction access memory references, IF and ID memory references. Only data access memory references, OF and WB memory references. Suppose question is how many memory references required to complete the instruction. Complete the instruction means fetch cycle plus execution cycle. So instruction accesses plus data accesses together called as the total memory references required to complete the instruction. Okay, so carefully read the question, try to understand whether question is expecting instruction accesses, data accesses or total accesses. Okay, accordingly you need to answer the question. What I mean to say is, knowing the concept is one aspect, understand the question is another aspect. When you know everything but you don't know what the question is expecting, then how can you answer the question? That is the reason, invest the time to read the question. Many students are not reading the question completely. Okay, partially they may read the question, they are worried about the solution. Okay, they are investing more time to solve the question, they are investing less time to read the question. Without reading the complete logic of the question, how can you solve the question? So try to read the question carefully, later solve the question. Okay, terminology is important. Alright. So here, when you are executing the instructions like this, okay, sometime we have a instruction formats. What is instruction format? Instruction format gives the layout design of instruction. Okay, that instruction format depends on the type of CPU. Already you know that. So instruction formats are 0 address format, 1 address format, okay, 2 address format, 3 address format. Like this, 4 formats are there. 5th format, 4 address format is not in the use. So why that is not in the use, you know already. Okay, so 4 address format name wise you have, but practically not in use. That is not in use. Okay, all right. So these formats are depends on the type of CPU. Depends on type of CPU. Okay, how many types of CPUs are present? Already you know that stack CPU, and you know that accumulator CPU, okay, and register to memory CPU, register to memory reference CPU, and last is register to register reference CPU. Like this, you have a 4 types of CPUs. Based on the ALU data path, type of CPUs are classified like this. Okay, so based on the type of CPU, instruction format is defined like this. Fine. So 0 address format, 1 address, 2 address, 3 address, 4 address. 4 address practically not present. These formats are classified based on type of CPU. CPUs are classified based on availability of ALU data. Already you know the characteristics of these CPUs, no need to elaborate that. Okay, so in this discussion we have one important concept named as the expand opcode technique. Expand opcode technique. Okay, in the expand opcode technique, first of all we need to understand what is the instruction size. Okay, here basic criteria is instruction size is fixed, that is fixed length instructions, and instruction formats are different. Instruction formats are different. What I mean to say is, to implement different instruction formats on a fixed length instruction CPU, expand opcode technique is used. Okay, procedure you know. In the expand opcode technique, first of all we should decide the opcode length of all instructions. Okay, after taking opcode length of all instructions, decide the smallest opcode, that is called as the primitive instruction. Next smallest derived instruction, next smallest further derived, and so on. So based on the opcode size, we are classifying the instructions as primitive, derived, further derived. Okay, after that we are taking the primitive format, identifying the total number of instructions possible. From that we are subtracting the existed instructions to get the free opcodes. Okay, now by using those free opcodes we are going to design the derived instructions. At the time of designing the derived instructions, compare the derived format with primitive format. After this comparison, take the common parameters as it is. Okay, non-common parameters merged with the free opcodes. Non-common parameters, how many bits are required, keep them as it is. Okay, how many bits are not required, those bits are merged with the free opcode. Therefore opcode length will be increased for the derived instruction. That is called as the expand opcode technique. In our regular session we solved many questions, many more questions in that expand opcode technique. Okay, everyone knows that, you all are familiar with that concept. Okay, so this is just refreshment. Also we are going to see the sample questions in this area, right? Because in the previous year GATE papers there are questions formulated based on expand opcode technique. Fine. Okay, after completion of the expand opcode technique, we have some important point that is called as the addressing modes, right? So addressing modes shows the, this is the addressing mode. Addressing modes shows the location of a required information. Fine. So what is the output of the addressing mode? Addressing mode output is effective address. Okay, so what the effective address indicates? Effective address indicates actual address of the requirement, actual address of a data. If you want data, this is the actual address of a data, or if you want instruction, this is the actual address of a next instruction. Is it okay? Like this. So effective address is the output of the addressing mode. So here we have the different addressing modes. Okay, immediate addressing mode. In the immediate addressing mode, what happens? Opcode and address. See, this is the instruction format. Usually this is the instruction design. So immediate addressing mode, listen, this address field itself a data. Okay, next, when it is a register addressing mode, then this address field is the effective address, that is the register name. Okay, that is the register name. Next, if it is a direct addressing mode, then it contain the address field contain the effective address, that is a memory address. Okay. Next, when it is a indirect addressing mode, then address will contain the effective address, that is a address of a effective address. Okay, address of an effective address. Okay, especially when it is a indirect addressing mode, address size is very important because this is not effective address. When it is a indirect addressing mode, this address will contain the address of effective address, address of an effective address. So that should be a memory address. Okay, when it is address of effective address, to access the effective address from the memory, address size become important parameter. When address size is one word, okay, one memory reference required to get the effective address from memory. When address size is 4 word, then 4 memory references required to get the effective address from the memory. So in the indirect addressing mode, number of memory references varies, depends on the address size. Okay, so when question contain indirect addressing mode, some careful attention required from the student side to answer the question. Otherwise, there is a chance to take the wrong prediction. Okay, there is a chance to take the wrong answer selection. Fine. Okay. Next, here this is a indirect addressing mode, correct? Suppose this indirect addressing mode is register indirect addressing mode, then address will contain address of an effective address, but that is the register name. Okay, so when effective address is in the memory, that is memory indirect, effective address is in the register, that is register indirect address. Very good. Next, when it is a indexed addressing mode, indexed, then address will contain what? Constant along with index register, along with RI. Okay, when it is a, suppose this is a auto indexed addressing mode, then address will contain plus or minus symbol along with base register. Is it clear? RB, base register. Okay, when it is a PC relative addressing mode or base register addressing mode, then here what you have? Relative value or displacement. This relative value or displacement will be adding to PC, that is the PC relative addressing. That relative value will be added to base register, that is the base register addressing. Like that, different addressing modes are present. So based on the addressing mode, this address behavior will be changed. This address field behavior, listen dear students, this address field behavior will be changed, depends on type of addressing mode. Immediate addressing mode, address will contain data. Okay, register addressing mode, address will contain effective address, and so on. Okay, so number of memory references varies according to the type of addressing mode used. Okay, already I explained the actions which are associated with addressing modes in your regular session. Okay, refer that. Fine. Next, when we are talking about the interrupt cycle, after completion of every instruction, that is fetch cycle, execution cycle. After completion of every instruction, okay, CPU checking for the interrupts. Interrupt verification is present. If interrupt is not present, then CPU fetch the next instruction like this. Okay, if interrupt present, yes, then CPU service the interrupt. CPU service the interrupt. Is it clear? After service the interrupt, again moving back to fetch cycle. So like this, interrupt cycle is connected at the end of the instruction cycle. This is instruction cycle and this is the interrupt cycle. After completion of every instruction, checking for the interrupt. If interrupt not present, go to next instruction fetch. When interrupt present, service the interrupt. Later go to the next instruction fetch. Okay, like this CPU executing the program along with interrupts. Okay, right. After this you may have the concept of RISC and CISC computers. Okay, reduced instruction set computer and complex instruction set computer. Okay, you know the differences between both the computers. Okay, when you know the characteristics of RISC computer, opposite characteristics are true in the CISC computer. Fine. RISC, more registers, less addressing modes, fixed length instructions, successful pipeline, CPI equal to 1. Okay, supercomputer, used in real-time application, expensive computer, smaller instruction set, using hardwired control unit, and we have the same meaning of Motorola processor, PowerPC processor, ARM processor. Opposite characteristics are true in the CISC computers. Okay, so please remember characteristics of RISC and CISC. They are also important. Okay, so another refreshment is what? Performance. If you want to calculate the performance of a CPU, what we want is simply execution time required. Execution time of the program is summation of IC subscript I into CPI subscript I whole multiplied with cycle time. This is the formula used to calculate the program execution time. Here performance of a CPU is inversely proportionate to execution time. Quick processing, more performance. That's what. Performance inversely proportionate to execution time. Okay. When you want to compare performance of one computer with another computer, we are using the speed up factor. So X is compared with the Y. So which system you are comparing? Okay, that system execution time should be denominator. So S equal to execution time of Y upon execution time of X. S indicates the speed up factor used. Okay, X is compared with Y. So performance of X upon performance of Y. Performance inversely proportionate to execution time. That's what execution time of Y upon execution time of X. So straight away you may use this. Whichever the system is compared with other system, okay, that system execution time should be denominator. X is compared with Y. So X system execution time is denominator because performance is inversely proportionate to execution time. Okay, so this much refreshment is enough to answer the questions which are related to computer architecture. So apart from this, if you see the regular class notes, you have the sequential concepts one by one. This is just refreshment. So I am giving you the basic information for the quick recap. Okay, very good. Now I am showing the questions. Please see the questions and give the correct answers like data representation. You all are given the right answers, right? The same manner you please give the correct answers in this topic also. Ready? Very good. See that. This is the question. Students, take the question and give the answer. Students, please consider the question and do it fast and give the right answer. I am waiting actually. Alright. So here what is mentioned? Consider a hypothetical CPU which supports one word opcode. They given one word opcode, one word register address and 4 word memory address. Instruction is designed with the following format. Yes, they mentioned everything clearly in the question. Opcode length is 1 word, register address is 1 word, memory address is 4 word. This is the instruction given. Okay, ADD, this is the opcode, this is 1 word. Let me take another color. Yes, this is ADD, addition. This is 1 word, right? Then register address. This is the register address. This is 1 word. Then memory address 4 word. This address, memory address 4 words, and memory address 4 words. Then where is the addressing modes? Addressing modes are implicitly implemented in the opcode. Opcode itself specifies type of operation along with the type of addressing modes. Already they mentioned destination, source 1, source 2. Okay, square brackets indicates direct addressing, @ symbol indicates indirect addressing. Number of memory references required to complete the instruction. They are asking completion. You know, completion means fetch cycle plus execution cycle. They are not asking only instruction accesses. They are not asking only data accesses. They are asking the total instruction complete accesses. So fetch cycle accesses and execution cycle accesses required. Please respond, my dear students. Give the right answer. I want correct answer. Rajat Bharati. Yes, Pratik Sagar. Please give the right answers. I am waiting. Yeah. Students, you already given the answers. Let me check whether they are correct or wrong, because different students given different answers. What I said earlier, when we have a indirect addressing mode, when you have a indirect addressing mode, again, when you have a indirect addressing mode, we need to fetch effective address from the memory. When you fetch effective address from the memory, compulsory address sizes matter. Address size is very important. Okay, please consider my request. Indirect addressing mode is present in the question. Every student is going to invest more attention, okay, to think about address size. If address size is not given, by default assume 1 word. Address size is given 1 word, then no problem, 1 MR. If address size is more than 1 word, then more than 1 memory reference is required. This is the logic in this question. Not only in this question, everywhere, wherever indirect addressing mode is present, compulsory you need to verify the length of address. Okay. Here in the chart section, different answers you given. Pavan, Pratik, yeah, okay. This is the exact difference, my dear. In the previous section where I explained the data representation questions, there all students are given the same answer. In the previous section, data representation, all students are given the same answer. But suddenly when I explain some conceptual question, different students are giving the different answers. Okay, okay. Here analysis is like this. Fetch cycle plus execution cycle. Fetch cycle plus execution cycle. This is the total completion, correct? Completion means both, right? You know the framework of that. What is the framework? Framework is IF, ID, OF, PD, WB. I explained this many times in your regular notes, right? This framework. To complete any instruction, it is having certain number of states like this. Yeah. So, what is the answer? See this. First thing, you should decide length of instruction. Bataiye, what is the length of instruction here? Length of instruction is one word. This is one word instruction, 4 word instruction, 1 word instruction, 4 word. These are the fields actually. 1 plus 4, 5, 5 plus 5. This is a total 10 word instruction. 10 word long instruction it is. Instruction size is 10 words. Very nice. Then come to the processing. In the processing, first of all, here one memory reference required to get the opcode. Decoding. Decoding tells it is a 10 word instruction. Because of 10 word instruction, 9 memory references required. Very good. Then source. Source 1, register addressing mode. Register addressing mode means 1 RR, register reference required. Then source 2, listen carefully. Source 2, using indirect addressing mode. In the indirect addressing mode, first access the effective address. Access EA, effective address. So here address size is how much? Address size equal to 4 words. Okay, so to access 4 word memory address, okay, how many memory references required? 4 memory references required. Many students are taking 1 MR here. Access effective address, 1 memory reference required. Okay, if and only if address size is 1 word. But here address size is 4 word. When it is a 4 word address, to access the address, 4 memory references required. Okay, after that access data. After that access data. Okay, data is nothing but a word. Data means word. Therefore, 1 MR required. This is the concept. Okay, the students whoever taken wrong here, that student answer is wrong. Okay, so this logic is required. Address size is 4 word. When it is a 4 word address, compulsory 4 memory references required to access effective address. Later you can refer the memory to get the data. Clear? Right. Next, PD. PD means one ALU operation, addition operation. Then destination. Destination using direct addressing. In the direct addressing, address field itself contain effective address. So only write the data. Write the data. Okay. So 1 MR required. That's it. 1 MR required. So now count the total number of memory references. How many are there? 10. See here 1 plus 9, 10, 14, 15 and 1, 16. Total 16 memory references required. Whoever given the answer as 16, that is correct. Whoever giving different answers, that is wrong. Clearly see this. Here source 1, source 2, destination. Everything is visible. Okay. Hope you understand, right? Pavan Kumar, your answer is correct. Okay, students, those who are giving the wrong answers, okay, you please realize your mistake. Please realize your mistake. Don't repeat that mistake in future. Okay, no? Those who are given right answers, well and good. Okay, if you given wrong answer, don't get demotivate yourself. Okay, try to understand where you misinterpret the question. Okay, where you miss the logic. Try to understand that. Work on that. Okay, therefore you never repeat such mistake in future if you realize that mistake now. Okay, very good. Then take next question. This is the question, please. Consider a hypothetical 64-bit CPU. They mentioned it is a 64-bit CPU which supports one word instruction. Actually, this is the instruction misprinted. One word instruction. Consider a hypothetical 64-bit CPU which supports one word instruction placed in 32 GB memory space. Okay, instruction is designed with 2 register operands, memory operand and immediate constant field. Okay, right. Instruction set size is 400. Register file size is 32. Range of signed constants possible in the instruction. This is what MCQ question. Please answer it. It's easy question. What is the answer? Hypothetical CPU. Okay. As a solution, if you see this, word length of a CPU is equal to 64-bit because it is a 64-bit CPU. 64-bit CPU means word length is 64-bit. Okay. Now, instruction size is equal to one word. They given one word. One word is equal to 64-bit. Okay. Then instruction is designed with 2 register operands, memory operand, immediate constant. See this instruction design. Okay. In the instruction design, what you have? Opcode. By default, every instruction contain opcode. Next, 2 register operands. Okay. Next, 1 memory operand. Next, 1 immediate constant field. This is the instruction format given. Clear na? So this is the 64-bit instruction. Fine. Next, number of operations. How many? 400. Log 400 base 2. This is equal to 9-bit opcode. Number of registers 32 given, right? Log 32 base 2, 5-bit. Log 32 base 2, 5-bit. Okay. Next, memory. Log 32 gigacells base 2. This is equal to 35-bit address. Is it okay? Next, immediate constant field. How many bits are used for the immediate constant field? Decide that. So, immediate constant field size is field size is equal to how many bits? 64 minus 9 plus 5 plus 5 plus 35. This is equal to 10 bits. Okay. This immediate field is used for signed numbers, signed data. Okay, signed data is by default 2's complement data. So 2's complement range minus 2 power 10 minus 1 to plus 2 power 10 minus 1 minus 1. This is the range. Okay, so now see that range is minus 5122 plus 511. This is the answer. Range of signed constants. Signed means default 2's complement. Default 2's complement data. So this is the range of signed data. Okay. So what is your answer? Correct answer is minus 512 plus 511. Yes, C is the right answer. Answer is C. How many of you given right answer? Let me see in the chat section. Yes, Pratik, Sagar, Rajat, Bharati. Yes, you all are given right answer. Thank you. Thank you. Jiban Krishna. Amit. Thank you, dear students. Next, take another question. So these all are the questions which are related to your computer architecture module. Okay. So if you see your regular running notes, there also we have the concepts along with set of questions. Now this is also the concept review over. Now I have given the some set of questions. Okay. You just see the question, give the answer. Let me see how many of you giving the right answer. This is actually 2 marks weightage question in the gate paper. Already in PYQ some set of questions formulated based on this kind of logic. Fine. So please read the question, give the answer. I am also reading along with you. Consider a hypothetical CPU which supports 24-bit instruction placed in 1 KB memory space. Instruction length is 24-bit that will be present in the 1 KB memory area. System supports A type, B type, C type instructions. Register file size 256. A type instruction is to address, see this, to address register reference instruction. B type instruction is to address memory reference instruction. C type instruction is to address register reference and 4-bit immediate constant field. Okay, to address register reference and 4-bit immediate constant. Okay, if there exist 28 A type instructions, 14 B type instructions, how many C type instructions are formulated? It's a numerical question. Okay, please solve the question, give the right answer. Okay, do it quickly. Along with you, I am also solving the question. Okay. Okay, right. So here what is given? Hypothetical CPU which supports 24-bit instruction. So here instruction size equal to 24-bit mentioned. Next, instruction placed in 1 KB memory, that is okay. Instruction formats given. Instruction formats. What is given here? A type instruction, B type instruction and C type instruction. 3 types of instructions given. So you know different formats, all formats uses same length, fixed length, fixed size. Then compulsory use the expand opcode technique. Expand opcode technique required. So this is the expand opcode technique question. Okay, right. So what is given here? A type instruction. This is A type. A type instruction is to address instruction like this. Opcode, two addresses, both are register addresses, register and register. Okay, to address. Fine. So here 24-bit instruction. Register file size 256 given. So 8-bit register address, 8-bit register address. Remaining 8-bit is the opcode. Then B type instruction. B type is also to address instruction, but that is the memory reference instruction. So both of the addresses are memory addresses only, like this. This is the 24-bit memory address, 1 KB memory, so that 10-bit address, 10-bit address, and remaining 4-bit is the opcode. Okay, right. C type instruction we have. In the C type there is a opcode, register address and immediate address value. This is given. Fine, right. So now here this is also 24-bit instruction. Okay, what they mentioned, immediate field 4-bit immediate they mentioned in the question. So 4-bit immediate, 8-bit register address. Okay, and remaining bits are opcode bits, 12-bit opcode. So according to question, I took A type, B type and C type instruction formats. Now compare the opcodes. Now I am going to compare the opcodes to decide the primitive, derived, further derived. So when I compare, this is 8-bit, this is 4-bit, this is 12-bit. You know, smallest opcode is primitive. This is primitive. Fine. Then next smallest is derived. Derived. Okay. Next one is the further derived, like this. Okay. Further derived. Very good. Now, what we need to do? First, compare the primitive with derived. Opcode, memory, memory. Here opcode, register, register. Okay, opcode, opcode common. So take opcode as it is. But here names are different, but addresses are required. This is 20-bit address, this is 16-bit address. So from this 20-bit address, okay, from this 20-bit address, we are going to allocate the 16-bit address for register. And after that, remaining bits, 4 bits merged with the free opcodes, like this. In the 20-bit address, 16-bit address required, remaining 4-bit address not required. That's what 4-bit address will be merged to free opcodes. Okay. Now come to derived and further derived. Derived, further derived, if you compare, so here opcode, opcode common, So take opcode as it is taken. Then after that we have a total here 16-bit address. In this 16-bit address, what we are going to do is we are allocating 4 bits for the immediate, allocating 8 bits for the register, and remaining how many? From the 16, if you take the 8 and 4, 12, and remaining 4 bits merging. Is it clear? So like this, take the primitive, from the primitive design the derived, from the derived design the further derived. This is the logic of expand opcode technique, you know that. So implement the logic to give the answer. So primitive format, opcode, memory address and memory address, like this. Okay, so 4-bit, 10-bit and also 10-bit. Fine. Next, number of operations possible is equal to 2 power 4, that is 16. 16 operations possible. But how many B type of instructions are present? Read this. How many B type? 14 B type of instructions present, 14. So here number of free opcodes, after B type instructions, equal to 16 minus 14. This is equal to 2 free opcodes. So use these free opcodes for the A type instructions. So number of A type instructions possible is equal to 2 into number of free opcodes are 2. How many bits are merged? 4 bits. So 2 power 4. So this become what? 32. 32 A type instructions possible, but how many are implemented? That is given in the question. Okay, 28 A type instructions are implemented already. So here number of free opcodes after A type instructions. Okay, that is equal to 32 minus 28. This become 4 free opcodes. These 4 free opcodes used for C type. So number of C type instructions possible equal to number of C type instructions possible equal to free opcodes 4 into how many address bits are merging? See this. 4-bit address merged with opcode. So 2 power 4. 4 into 2 power 4. Okay, that is 2 power 6. That becomes 64. 64 is the answer. How many of you given answer? Correct answer? Let me see in the chart section. Okay, this is actually the answer. 64 C type instructions are formulated after implementation of A type and B type instructions in the system. Okay. Yes. Shambhav, you given right answer. Pavan given right answer. Pratik given right answer. Dhruv Sharma given right answer. Rajat, Siddhi. Yeah, thank you so much. Okay, according to your communication, you all are given right answer. That means expand opcode technique question perfectly present in your brain. Very good. This is the actually question, expand opcode technique question. I am just showing you the question once again. Okay, right. This is the analysis of that question. Okay, thank you so much, dear students, for your prompt response. Right, you please utilize this session for the quick refreshment of this subject. Okay, maybe it is a actually allocated time is 5 hours, but in this 5 hours you may cover all the concepts by the respective faculty. Okay, because I only explained computer organization and architecture subject in the regular class notes. Okay, so when I am going to refresh the concepts, okay, background, in your background it is giving the feeling that again class is going to be repeated. If that is the case, your revision time will be saved. Okay, so don't think that sir our time is wasted at the peak end. No, your time is not wasted, your time is saved, because faculty only explain the review of all your concepts. Okay, so your revision time will be reduced. That's what, utilize the time properly. Now this is the question actually. See, this is my handwritten question. All of you please go through the question and give the right answer. This is also one nice question, which is different from your running notes questions. Smiley Ram, thank you so much. Yes. Consider the following code executed on a 2 nanosecond. This is the 2 nanosecond clock cycle 16-bit CPU. Consider the following code executed on a 2 nanosecond clock cycle 16-bit CPU. Cycle time given, CPU also given. Okay, this is the code. We have a 7 instructions, size given in bytes. Okay, all right. First instruction 6 byte, second instruction 4 byte, third 4, fourth 8 byte, fifth 6 byte, sixth 6 byte, seventh 2 byte. Very good. Instructions given with a respect to size in bytes. Okay, instruction fetch and decode takes, fetch and decode together they given, takes 3 cycles per word. 3 cycles per word. Instruction execution takes 6 cycles irrespective of opcode and addressing mode used. Irrespective of opcode, irrespective of addressing modes, every instruction on average takes 6 cycles to complete execution. Fetch and decode and execution, they given separately. Fine. Interrupt occurred during the execution of OR instruction and MUL instruction. At the time of executing OR instruction, at the time of executing MUL instruction, interrupt occurred in the program. Okay, interrupt processing time is 24 cycles. Dear students, in on screen you observed something na, some box is visible while my explanation, that is like a interrupt only. So whenever that box is visible, I click OK, then only my cursor will be moving into the respective sequence. So that's like a interrupt only, correct? So here interrupt occurred during execution of OR instruction and MUL instruction in the program. Interrupt processing time given 24 cycles. So program execution time is, they are asking program execution time. How much time is required to complete the program? This is the question. Usually question is lengthy, but nothing is there in the question. So question readability time is more, but requirement time required to solve the question is less only. Okay. So first thing what you need to do is convert this bytes into word. It is a 16-bit CPU, correct? When it is a 16-bit CPU, word size equal to 16-bit. 16-bit. Okay. So that is nothing but 2 bytes. 2 bytes equal to 1 word. Okay. So this is the 3 word. This is the 2 word. This is also 2 word. Okay. This is what? 4 word. 3 word. 3 word and 1 word, like this. Fine. Now come to the concept. What the concept says? Fetch cycle, execution cycle, after this checking for interrupt, if interrupt present, service the interrupt. If not present, simply go to the next fetch. This is the concept, right? Now apply this concept, solve the question. So here first I1 is fetched, I1 is executed, check, I1 is executed, check for interrupt, no interrupt. Now again I2 fetched, I2 executed, check interrupt, no interrupt. I3 fetch, I3 executed, check interrupt, no interrupt. Okay, now see what is I3 actually? Add. Next I4, I4 fetch, I4 execute. What is I4? OR instruction. So after execution, CPU checking for interrupt, yes, then service required, interrupt service. Next I5, I5 no interrupt present. I6, I6 is the MUL instruction. Okay, I6 is the MUL instruction. After I6 checking for interrupt, yes, interrupt present, so service interrupt. Service. Then I7, I7, okay, no interrupt, stop the execution. This is the concept here. Fine, dear students. So now we are going to execute the program in a respective sequence. What they given here? 2 nanosecond clock cycle given. Okay, fetch and decode 3 cycles per word, execution 6 cycles. Right? Now listen here. Let me take like this. Fetch and decode and processing. This is customized order according to our question data, like this. Number of instructions: I1, I2, I3, I4, I5, I6, I7. Okay, so size of instruction already specified: 3 word, 2 word, 2 word. Okay, so that means 3 word into 3 cycles, 2 word into 3 cycles, 2 word into 3 cycles, 4 word into 3 cycles. Okay, next 3 3 1, 3 word into 3 cycles. Fine, 3 word into 3 cycles. Correct, 1 word into 3 cycles. So processing for every instruction irrespective of opcode 6 cycles required. like this, 6 cycles processing. Every instruction processing. Halt instruction, you may think like this, sir, halt instruction decoding के बाद processing. Okay, so they mentioned in the question, that's what I taken. Okay, decoding के बाद execution over. Yes, that execution itself taking 6 cycles. They mentioned every instruction. They are not saying that halt is excluded. That's what I included halt. If they are saying halt is not taking any cycles, then exclude that. If that nothing is given, every instruction is taking 6 cycles for processing. Okay, all right. Some students may have the doubt, sir, halt के लिए processing क्या है? Okay, PC updated with the target address is a processing. Okay, so processing, they mentioned clearly in the question, every instruction, irrespective of opcode, irrespective of addressing mode, on average taking 6 cycles. That's what we taken, 6 for every instruction including halt. Okay, all right. But here interrupt occurred during execution of I4. Here interrupt occurred, so servicing required. Servicing 24 cycles. MUL interrupt occurred, servicing required 24 cycles. Bus. Now calculate the execution time. What is the execution time? Please add this. Okay, 15 cycles. Okay, 12 cycles. 12 cycles. This is 12 plus 6, 18 cycles. After that 24 cycles, then 15 cycles, then 15 cycles, after that 24 cycles extra, then 9 cycles. Okay, then program execution time equal to number of cycles into cycle time. Okay, calculate that. What is the answer? 288 nanoseconds. This is the answer. Okay, students, how many of you given the right answer? Let me see. This is the detailed explanation which I given. Okay, once you know the concept, directly by looking at the question, you need to put the numerical values, you may give the answer. Students are doing the question within a less amount of the time when you know the concept. Okay, this is the explanation given by faculty. That's what I take in the detailed explanation. Okay, all right. So answer is 288. Okay, thank you. Shambhav, Pratik. Okay. See the next question. This is the question. All of you please read the question. Consider 16-bit hypothetical CPU which supports 4 GB RAM. CPU 16-bit hypothetical, 4 GB RAM, 256 registers with a register wide of 16 bit. Okay, CPU contain one word opcode instructions designed with different addressing modes implicitly. Okay, opcode itself contain the type of operation and addressing mode. Right, index register is also present in the register file. This is the code given: I1, I2, I3, I4, I5, I6, I7. Okay, number of bytes required to store the program in the memory. Okay, so we need to identify the program storage space in bytes. So how much storage space is required to store the program? Tell me. So here what is mentioned? CPU, 16-bit CPU. Okay, all right. Word size is equal to 16-bit. Okay, 16-bit word is nothing but a 2 bytes. All right. 256 registers. Register address is equal to log 256 base 2. This is equal to 8 bit. 8 bit is nothing but 1 byte. Done. Then memory capacity, memory address, what they given? Memory address equal to 4 GB. Sorry, 4 GB capacity. So memory address is log 4 gigacells base 2. This is 32 bit. 32 bit is nothing but 4 bytes. Okay, all right. So instruction opcode size 1 word. So here opcode size equal to 1 word. 1 word is nothing but 2 bytes. Done. Very good. Now we need to find out the total number of bytes required to store the program. Fine. So here listen. This is the opcode, correct? This opcode 2 byte long. Register 1 byte long. Okay, address 4 byte long. Like this, identify the length. So instruction 1 size equal to 2 plus 1 3, 3 plus 1 3 plus 4 7 bytes. Next instruction 2, this one, opcode 2 byte, register 1 byte, address 4 byte. This is also 7 byte instruction. Then opcode 2 byte, register 1 byte, register 1 byte. Okay, this is I3 4 byte long. Then I4 opcode 2 byte, register 1 byte, register 1 byte. I4 is also 4 byte long. Then I5 opcode 2 byte, address 4 byte, address 4 byte. This is equal to 10 byte. I6, this is opcode, address, 8-bit constant, index register. See, opcode, this is a 2 byte. Opcode 2 byte. Address 4 byte. 8 byte constant, that is 1 byte. Register address 1 byte. Okay, index register. Register address is 1 byte. Constant size is 1 byte. Address size is 4 byte. Opcode size is 2 byte. So total 6 plus 2, 8 byte. Then I7 halt, only opcode. Only opcode is 2 byte. That's it. Now program size equal to program space is equal to, add all those, report the value. This is 42 bytes, correct? How many of you given right answer? Please respond. This is the question and this is the analysis, okay? Yes. Sayan Kumar, Shambhav, you all are given right answer. DGS, correct answer. Thank you. Yeah. What does register YD 16-bit? Some student asked that question. Register YD 16-bit means, let me draw this. 256 registers with a register wide of 16-bit. Actually, register will be storing the value, correct? This is the register file. To confuse the students, that is given there like this. These are the registers actually. R0, R1, R2 and so on. R255. Like this, total number of registers are 256. In every register, how many bits space is there? 16-bit space. 16-bit. 16-bit. This is the space actually. Space. Okay, wide, matlab width of the register. Inside the register, you can store 16-bit data. Like that, how many registers are there? 256 registers are there. 256. So, address is equal to log 256 base 2. Bus. This is 8-bit address. By using 8-bit address, you may refer the register. Okay. After referring the register, inside the register, 16-bit information is there that you may access. Okay. Very good. Now, next question please. This is the question. Please respond. Consider the following memory contents. These are the memory contents. Memory content of 4000 is 48. Memory content of 2000 is 6000. Memory content of 6000 is 62. Memory content of 3000 is 4000. Following instruction is executed in a 32-bit hypothetical CPU. Some CPU given. This is the instruction. Uses standard syntax. What is the standard syntax? Standard syntax means first parameter is opcode. Every machine instruction having the standard syntax like this. First parameter is opcode. Second parameter is the source 1 as well as the destination. And third parameter is the source 2 like this. This is the standard syntax. Okay. So, which of the following statements are true after the completion of an instruction? Okay. Execute the instruction, you may get the answer. Which of the following statements are true? So, you all are given the answer. Thank you, thank you, thank you. See this. This is the question actually. Addition operation. M of 2 square brackets enclosed with 2000. Okay. Loaded with M of 2 square brackets enclosed with 2000 plus source 1. M of 4000. Okay. So, here what is the value present? See this. 4000, M of 4000, because direct addressing mode. 4000 contain 48 base 10. Then M of 2000, 2000 contain 6000, right? Now 6000 contain 62. So 48, 62, that is 110. 110, correct? Now this will be stored in the memory. 2000 contain 6000. Okay, so 6000 location already have 62. Now that 62 will be updated with 110. Bas. This is the analysis of the question. So now go to the option, select the right answer. Memory content 2000 is updated with 110. This is wrong statement, correct? This is wrong. Then memory content of 6000 is updated with 110, correct? Memory content of 4000 is updated with 110, no. Memory content of 3000 is updated, no. So right answer is B. So already students given the answer. Okay, many students already given the answer in the chat room before my explanation. That means you know the syntax of the machine instruction. Very good. See this question. This is the next question. Verify. Consider a system used to process the addition operation which takes 4 nanoseconds. Addition operation takes 4 nanoseconds. Application program contain the addition of two vectors with a size of 100 elements. Two vectors with a size of 100 elements each, that is 100 elements each, that is A of 100, B of 100. So we need to perform the addition between these two vectors. So that 100 elements we need to add. Same program is executed on an alternative system which contain 5 processing units, 5 ALUs, which are operated in parallel. Okay, 5 ALUs are there, they are operated in parallel. Performance gain of an alternative system to run the program over the old system. Assume in the alternate system addition operation takes 6 nanoseconds. What is answer? Okay, so what is this meaning? Very simple question. Here we need to perform addition. So vectors given A of 10, sorry, A of 100, B of 100. So when we are going to add the operation, that is A of 0 plus B of 0. Okay, like this, A of 99 plus B of 99. So for every addition operation takes 4 nanoseconds, like this, 4 nanoseconds for every operation. So execution time of old system is equal to 100 into 4 nanoseconds. This is 400 nanoseconds. Okay, right. The same operation takes place on alternative system where we have a 5 ALUs operated in parallel. So when addition operation, addition data given to the CPU, okay, at a time 5 addition operations are running in parallel. At a time 5 addition operations are running in parallel. Then what will happen? In alternate system, okay, 5 operations are running in parallel. So execution time is equal to execution time of alternate system equal to 100 divided by 5. So 100 operations are sharing into every operation taking 6 nanoseconds. So what is the value? Report that. This is 120 nanoseconds. Number of computations are 100, but their 5 operations are running in parallel. So 100 divided by 5 into 6 nanosecond. Now speed up. They are asking performance gain of a alternative system. So S equal to execution time of old upon execution time of new. This alternative system is new system. So S equal to 400 upon 120. Do the calculation, report the value, conclude the answer. 400 upon 120. This is equal to 3.33. Yes. Go to the question, select the answer. 3.33, that is D. Answer is D. Okay. Like this, you need to calculate the generalized question. Actually, this is a generalized question. Logic is given in the question only. By observing the logic, you may get the answer. Okay. Yeah, you please verify this alternative system addition operation takes 6 nanosecond, not 4. 6 nanosecond. Old system addition takes 4 nanosecond. So 100 additions, each addition 4 nanosecond, that is 400 nanosecond. Alternative system, each addition takes 6 nanoseconds. Each addition takes 6 nanosecond. But how many number of additions? Actually 100. Okay, there 5 operations are running in parallel. Okay, so that this is the answer. You please cross-examine your answer. Okay. Rajit Bharati. Our answer is D. Is it okay? Next. See this question. Okay. Now see this. In the question, what is given? Consider 3 nanosecond clock cycle CPU which consume 4 cycles for data transfer instruction, 8 cycles for ALU instruction, 6 cycles for branch instruction. Given clearly. Relative frequencies of these instructions 30%, 60%, 10%. Okay, total 100%. This is relative value. System is enhanced with respect to speed ups of 2, 1.6 and 2. Okay, respect to speed ups of. That means what? Data transfer operations speed up is 2. Data manipulation operations speed up is 1.6. Branch operations speed up is 2. Performance gain of a enhanced system. Okay, now we need to calculate the speed up factor. So here first execution time of old system is equal to summation of IC subscript I into CPI subscript I whole multiplied with cycle time. Apply this. Okay, then what is the value? 0.3, 30% data transfer 4 cycles plus 60% ALU operations 8 cycles plus 10% branch instructions 6 cycles. The overall cycle time of the computer is 3 nanoseconds. Okay, calculate the value. One point 2 plus 4.8 plus 0.6 into 3 nanosecond. This is 19.8 nanosecond. Please cross examine. Okay, next, what is given? ALU operations are enhanced. Now see this. Data transfer, ALU as well as the branch. First data transfer, DT, data transfer. S is equal to execution time of old upon execution time of new. After enhancement, speed up is given. So 2 is the speed up. Old time is 4 cycles divided by new time. Okay, so execution time of new is equal to 4C divided by 2, that is equal to 2 cycles. Similarly, ALU instructions, speed up S equal to old time is 8, new time is 1 point, speed up is 1.6. So here execution time of new, we want a new time. So here speed up S equal to ET old divided by ET new. So that is 8 is equal to, what is the speed up given? 1.6. 1.6 equal to 8 cycles divided by execution time of new. So execution time of new is equal to, okay, 8 cycles divided by 1.6. So that is equal to 8 upon 1.6, that is 5. Similarly, branch instructions. Speed up given S equal to ET old upon ET new. Okay, so 2 is equal to 6 upon ET new. Therefore, ET new is equal to 3 cycles. Okay, fine. 3 cycles. Clear? Very good. Now apply the formula. Calculate the overall execution time. This is the execution time of new computer is equal to 30% data transfer instructions into 2 cycles plus 60% ALU instructions into 5 cycles plus 10% branch instructions into 3 cycles. The overall cycle time is 3 nanoseconds. Okay, all right. Now do the calculations. 0.6 plus 3 plus 0.3 into 3 nanoseconds, that is 3.9 into 3 nanoseconds. Okay, 3.9 into 3, that is 11.7, nanosecond. Clear? Now what is the speed up? Speed up equal to S is equal to 19.8 nanoseconds upon 11.7. 19.8 upon 11.7, that is 1.69. This is the speed up. What is the performance gain of enhanced system? 1.69. Okay, you please cross examine the calculations. How many of you given right answers? Answer is 1.69. Okay, so like this we are going to calculate the performance gain of a system, right? Old system execution time and new system execution time both are calculated, later reported the performance gain, that is calculating the speed up factor. Alright, so after completion of this computer architecture refreshment, we are moving on to the computer organization. In that computer organization, I am going to concentrate on the pipelining concept. Okay, so already you know the implementation of the different organization concepts, that is computer system is having the three fundamental components: CPU, memory and IO. Inside the CPU we have a different components named as the registers, ALU, control unit. So what are the registers present in the computer? Okay, then what is the functionality of each register, already known to you. After that, ALU data paths, stack CPU, accumulator CPU, register memory CPU, register CPU, that is also known to you. Then next one is control unit. Control unit is implemented by using two methods: hardwired control unit and microprogrammed control unit. So in the hardwired control unit, control signal is expressed in a sum of product expression format. In the microprogrammed control unit, microprograms are permanently stored in the control memory, that is ROM. That ROM is programmed either with vertical microprograms or with horizontal microprograms, so that microprogrammed control unit further divided into two types: horizontal microprogrammed control unit and vertical microprogrammed control unit. Okay, in that vertical control unit, encoded formatted control signals present. In horizontal control unit, decoded formatted control signals present. So when the control signals are directly represented with a decoding format, it will take more space and it is very complex to design. That's what horizontal is practically not present. Okay, vertical is implemented in the CISC computers. So altogether we have only two practical control units. One is the hardwired, that is used in the RISC computer. Second is the vertical control unit, that is used in the CISC computers. So that is related to just control unit implementation. After that, enhancement of a computer, there we are focused on the pipelining. Okay, now I am going to take the detailed analysis of the pipelining. Let me give the refreshment of pipeline formulas. Later we will see the questions in that area. Okay, very good. Okay, so here, before moving on to the questions of a pipeline, let us see the just overview of the pipeline. Okay, so you know that pipelining concept allows the overlapping execution. This is first thing. Pipelining allows overlapping execution. Okay, second thing is pipeline execution time is equal to K plus n minus 1 into Tp. This is the formula if and only if n is finite. Okay, right. Next, if n is infinite, n is approach to infinite, okay, then CPI is equal to 1. You know that. Fine. When the n is not given, then we take CPI equal to 1. Where n is given, then we take k plus n minus 1 into Tp is the formula. Right. Speed up factor S is equal to n into Tn upon k plus n minus 1 into Tp. This is the formula to calculate the speed up of a pipeline over non-pipeline system. Okay. So where n is finite. Next, S equal to Tn upon Tp. This is the formula to calculate the speed up where n is infinite. Okay, right. Next, S equal to K. This is the formula where efficiency equal to 100%. You know this. Next, efficiency of the pipe is equal to S by K. And throughput of the pipe, you know, number of tasks, n tasks are processed in a time of k plus n minus 1 into Tp. So these are the generalized formulas used in the pipeline to calculate the performance gain of a pipeline. Okay. So here cycle time Tp, cycle time is adjusted according to the pipeline stage delays. Tp is the cycle time. Okay, Tp equal to stage delay when you have the uniform delay pipeline. So Tp equal to maximum of stage delay. Okay, when you have the non-uniform delay pipeline. So Tp is equal to maximum of stage delay plus buffer delay. Stage delay and buffer delay together. Okay, then cycle time is equal to cycle time plus overhead, setup time overhead. If any overhead is mentioned in the question, then we are taking the adjustment of the cycle time. So these are the cycle time adjustments. Okay, after that, when you see the implementation of the pipeline, there we used the risk pipeline. In the risk pipeline, 5 stages are present: IFID, EX, MA, WB. Okay, so in that pipeline, when we are executing the program, there is a possibility of dependency. So dependency is a major issue in the pipeline. There are 3 types of dependencies present in the pipeline: structural dependency, data dependency and control dependency. 3 types. Dependency is the major problem. Okay, so this dependency problem causes the stalls. Stalls are nothing but extra cycles in the pipeline. Okay, so these dependencies are 3 types: structural dependency, data dependency and control dependency. Okay, so whatever the stalls created based on the dependency called as the respective stalls: structural stalls, okay, data stalls and control stalls. Okay, whenever dependency present, output is missing. When you want output, we need to handle the dependency. When we handle the dependency, extra cycles are created in the pipeline. Those extra cycles are called as the stalls. To minimize the stalls, we have a different techniques. Okay, they are renaming technique for the structural stalls minimization, operand forwarding technique for the data stalls minimization, and delayed branch technique, branch prediction technique, minimization of the control stalls. So like that, we have a different mechanisms to minimize the stalls. We don't have the mechanism to remove the stalls completely. Okay, so these are the optimization techniques. Okay, so there is no 100% efficiency possible because of stages are never be a uniform delay pipeline stages, and dependency is never eliminated. That is the reason 100% efficiency never expected from the system. We are tries to move towards 100% efficiency, but we never become 100% efficient, because in the real life implementation, pipeline stages are non-uniform delay stages and dependencies are compulsory present in the pipeline. Due to these two reasons, okay, no system become 100% efficient. Okay, all right. And after this, here I am not going to explain what is data dependency, what is structural dependency, what is control dependency, because already you know these concepts and these terms in your regular session. Okay, so in general, if you say structural dependency, resource conflict is called as the structural dependency. Okay, data dependency means read before write. Okay, instruction J reading the data before instruction A writes. Okay, that is data dependency. Control dependency means unwanted instructions are inserted into a pipeline before getting the target address. Okay, that is the control dependency. Unwanted instructions are inserted into a pipeline before getting the target address. Clear na? So when you see the data dependency, in that we have a true data dependency, anti data dependency, output data dependency. True data dependency means read before write. Anti data dependency, write before read. Output data dependency, write before write. Okay, so these all dependencies causes the data loss. To handle the data loss, we are performing the operations after. So read before write, problem. Read after write, no problem. But when we are doing the operation after, it creates the stall. That stall is called as the hazard. Okay, RBW creates RAW hazard. WBR creates WAR hazard. WBW creates WAW hazard. Okay, dependency is a problem. Okay, when you want to handle the problem, compulsory stalls are created. Those stalls are called as the hazards. Okay, so there is no technique present to avoid the stalls. We have the techniques to minimize the stalls. Okay, so when stalls are present, compulsory performance will be affected. Then how to calculate the performance? Like this: execution time of the pipeline with stall, that is 1 plus number of stalls per instruction into TP. Okay, so why we are taken 1 here? 1 taken because n is approach to infinite, or else n is approach to 100%. Where n is infinite or relative value, we are using this. Where n is finite, k plus n minus 1 formula is used. Okay, all right. Next, speed up. K upon 1 plus number of stalls per instruction. This is the formula. K upon 1 plus number of stalls per instruction. This is used when the pipeline is uniform delay. Uniform delay pipeline. Then S equal to Tn upon 1 plus number of stalls per instruction into TP. This is the formula to calculate the speed up when pipeline is a non-uniform delay. Okay, like this we have the different formulas to calculate the performance gain of a pipeline. Okay, all these formulas are well known to you. Okay, so we are using these formulas while solving the questions. Fine. So this is the refresh of the pipelining concept. So let us see the questions related to this. Yes, this is the question first. This is the MSQ question. All of you see the question and give the answer. Consider the following pipeline. Here pipeline given. Number of stages 5 stages and also instruction delays given. That means buffer delays given. Stages given with stage delay and buffer given with delay. Which of the following statements are false? False statements we need to identify. False. Fine. In this design, pipeline takes more time to complete one task compared with non-pipeline. Pipeline takes more time to complete one task compared with non-pipeline. This statement is true. Reason is what? This is a non-uniform delay pipeline. See this? Execution time of pipeline is equal to k plus n minus 1 into Tp. Because n is equal to 1. They given n equal to 1. So 5 plus 1 minus 1 into Tp. Tp means stage delay plus buffer delay, maximum value. What is that? Here last stage does not contain the buffer. So here don't add the buffer delay to last. So this is equal to 45 nanoseconds. Okay. Then execution time of non-pipe. In the non-pipe what will happen? Only Tn. Okay. That is S1 plus S2 plus S3 plus S4 plus S5. So there is no buffer delay present here. Okay. So what is the value? 4 plus 6 10, 10 plus 2 12, 15, 24. So non-pipeline taking less time, pipeline taking more time with respect to one task. So this statement is true. And second statement, what is given? In this design, pipeline takes less time to complete 40 tasks. Compared to non-pipeline. Yes, this statement is also true. True statement, true statement. Okay, why 40 tasks takes less time? Because when number of tasks are increases, overlapping execution takes place. That's what pipeline taking less time. Then in this design, pipeline takes 45 nanoseconds and non-pipeline takes 24 nanoseconds to complete one task. Yes, this statement is also true. Already we identified. True. Okay. Then in this design, pipeline cycle time is 10 nanoseconds. This is false. False statement. Okay. So only one option is matching here. That is D. D is the answer. Because here last stage is having, see this, last stage 9 nanosecond. It does not have the buffer delay. So that is the reason cycle time is 9 nanoseconds only here. Tp is equal to maximum of stage delay plus buffer delay. That is 9 nanoseconds. So which of the following statement is false? Answer is D. Fine. Next. See this question. See this question. Consider the following pipeline. Here they mentioned pipeline. Total 5 stages present and also there is a buffer at the end of last stage. Okay. Then what is the cycle time? Tp is equal to maximum of stage delay plus buffer delay. So this is 10 nanosecond, this is 6 nanosecond, 12 nanosecond, this is the 6 nanosecond, this is 14 nanosecond. So that TP is equal to 40 nanosecond. Maximum of stage delay plus buffer delay. Together we are taking, correct? This is this one like this. So TP is equal to 40 nanosecond. So which of the following statements are correct? So we need to identify the correct statements. Pipeline cycle time is 12 nanosecond. This is false statement. False. Okay. Then pipeline cycle time is 40 nanosecond. Yes, this is true. Okay. Pipeline takes 40 nanoseconds to complete the instruction when very large number of instructions are executed in the pipeline. Is this statement true or false? Very large number means n is approached to infinite. When n is approached to infinite, CPI of the pipeline is equal to 1. Where n is approached to infinite, CPI of the pipeline is equal to 1. CPI of pipeline is 1 means, so what is the time here? 1 cycle means 40 nanoseconds. So this statement is true. True statement. Fine. Pipeline takes 1456 nanoseconds time to complete 100 instructions. Now take the execution time. Execution time equal to K plus n minus 1 into TP. Okay. So K value 5 plus 100 minus 1 into 14 nanoseconds. Okay. Do the calculations. 104 into 14. 1456 nanoseconds. Correct. So pipeline takes 1456 nanoseconds time to complete 100 instructions. Correct. This statement is also true. Okay. So which of the following statements are true? So answer is B, C, D. B, C, D. That is the right answer. Let me see how many of you given right answer. Okay, right. So now I am giving you the next question. Yes, this is usually 2 marks weightage question in the paper. So all of you try to solve this question. Do it quickly. This is the operand forwarding technique question. Rajat Bharti या Pratik Sagar. Operand forwarding technique question. It is. What is mentioned here? 5-stage pipeline given. It is a 5-stage pipeline. IF, ID, OF, PD, WB with 2 nanosecond clock used to execute the program. Total 5 instructions present. All instructions are spending 1 cycle on all stages, but ADD instruction takes 3 cycles, SUB takes 4 cycles, and multiplication takes 2 cycles on PD stage. Okay. Time saved to execute the code with operand forwarding over without operand forwarding. Okay. Usually it is a 2 marks weightage question in the paper. How to solve this? First formulate the information. What is that? IF, ID, OF, PD, WB. Sorry. Total 5 stages are there. WB. Number of instructions I1, I2, I3, I4, I5. 5 instructions present. Okay. So every stage taking one cycle like this. One cycle. But ADD instruction take 3 cycles. First instruction ADD, fourth instruction ADD, 3 cycles. SUB takes 4 cycles. Okay. MUL takes 2 cycles. 2 cycle. DIV 1 cycle. Yes. So this is the information given in the question. Accordingly, we formulated the table. Okay. Next, identify the dependencies. Instruction 2, R4, R5 input parameters, they are not matching. So I2 is the independent instruction. I3 matching, so that I3 dependent on I2. Input register, output register compared, matching, correct? Next one, I4 input register, I3 output register matching, so that I4 dependent on I3. Okay. Next, I5 R7 matching, correct? Now I5 dependent on I4. So there is a data dependency present between I3 to I2, I4 to I3, I5 to I4. Okay. So now we need to execute this program with operand forwarding and without operand forwarding. Here we have a logic. Okay. Optimized logic, that is without drawing the table we are concluding the answer, and without optimization, that means we draw the space-time diagram to solve the question. Okay, 2 methods are there. Optimized method to solve the question, without optimized method. Fine. So let me explain the optimized method first. Without drawing the table, how we are going to solve the question. With operand forwarding. Okay, so here instruction 1, 2, 3, 4, 5. Total 5 instructions are there. So 5 inputs. Because of dependency, there may be a stalls. Now we are going to calculate the stalls here. We are going to calculate the stalls. So first instruction independent, there is no stall. Second instruction independent, correct? See this. Dependency detected in the ID stage. Here dependency. But data access happened in the OF stage. See that. Data access required in the OF stage. So where the data access required, that is important in the data dependency. Wrong data injected into a pipeline, that is the data dependency problem. Okay. So now in this question, operand fetch takes place in the separate stage, not in ID. So here this is the operand fetch. Here no data dependency. This operand fetch is overlapping with PD here. Okay. So one cycle overlapped and 2 extra cycles present. That means 2 stalls. These 2 stalls are called as the structural hazards. These are the structural hazards. Why they are structural hazards? Because there is no data dependency between I2 and I1. Data dependency not present, but structural dependency present. Stage is not available. PD stage is not available for I2. That's what I2 will be waiting until the stage become available. They are the structural hazards, right? Then come to the I3. I3 data dependency detected in the ID. Operand fetch takes place in the OF. So it is data dependent on I2. So OF is overlapping with PD. OF taking 1 cycle, PD taking 4 cycle. 1 cycle overlapped. So extra cycles are 3. So 3 stalls. These are the data hazards. Okay. When data hazard is present, no need to count the structural hazard. Okay. When data hazard is not present, we need to count the structural hazard. Okay. Instruction is waiting for the stage. That is the structural hazard. Next please. I4. Data dependency detected in the ID. Operand fetch takes place in OF. So OF overlapping with EX. So in the EX data available, here data available, but OF taking 1 cycle, EX taking 2 cycle. 1 cycle overlapping. So extra cycle is 1. So that 1 stall. Now come to I5. Data dependency detected in ID. Operand fetch takes place in OF. So OF is overlapping with PD. Here data available because of operand forwarding. Data available at the end of PD. OF taking 1 cycle, PD taking 3 cycle. 1 cycle overlapping. So extra 2 cycles. That is 2 stalls. That's it. Then I5 all stages taking 1 cycle. Therefore, there is no stalls, extra stalls in the I5 separately. Clear? So now total number of stalls are 2 plus 3 5, 5 plus 3 8. 8 stalls present. Okay, 5 plus 8. So n is equal to 13. 13 is a finite number. Therefore, execution time is equal to k plus n minus 1 into Tp. So that is 5 plus 13 minus 1 into 2 nanosecond. What is the cycle time given here? 2 nanosecond. Okay. So what is the final value? 17 into 2. 34 nanoseconds. Right. Now this is with operand forwarding. Now let us see without operand forwarding. Without operand forwarding. Okay. So now total I1, I2, I3, I4, I5. 5 inputs present. Number of inputs are 5. Okay. 5 inputs. After that, stalls. Come to the I1. This is independent. There is no stall. I2. There is no data dependency but structural dependency present. Structural dependency stalls as it is. There is no change. Structural stalls are as it is. Okay. Alright. Next I3. I3 is a data dependency. Okay. Listen here. Without operand forwarding means first complete I3. After that, in the next cycle, we have the data. Here data reading takes place. So here 1 cycle overlapping with 4. Remaining 3. 3 plus 1, 4. 4 plus 1, 5. So here we have a 5 stalls because of the data dependency. Next, I4. 1 cycle overlapping with 2. Then extra cycles are 1. 1 plus 1, 2. 2 plus 1. Next cycle. 2 plus 1, 3. 3 stalls. Right. Next. 1 cycle overlapping with 3. So one cycle overlapping, extra cycles are 2. 2 plus 1, 3. 3 plus next cycle 1, 4. 4 stalls. That's it. So number of inputs are 5 plus extra stalls are, calculate this, 7, 3, 10, 4, 14. 14 stalls. So n value is equal to 19. N is equal to 19. So 19 is a finite value. Now calculate execution time. Execution time k plus n minus 1 into Tp. So k value 5 plus 19 minus 1 into cycle time. Cycle time is 2 nanosecond. Do the calculation. That is 36 nanoseconds, right? Not 36. (46 nanoseconds). Then how much time is saved? Time save equal to (46 minus 34). That is 12 nanoseconds. That is the answer. Okay students, like this we are going to solve the operand forwarding without operand forwarding questions. Without operand forwarding means we are reading the data after completion. So in the next cycle, after WB, in the next cycle we are reading the data. This is the answer. Let me see how many of you given the right answer. Okay. Similarly, I'll give the one more question. See this. See this question. This is also operand forwarding and without operand forwarding question. Okay. So if you are not comfortable with the optimistic logic without drawing the space-time diagram, then you draw the space-time diagram and calculate the value. So drawing that space-time diagram, computing the value taking more time. That's what practice the logic like this. Okay. Right. Consider 6-stage pipeline. They given 6-stage pipeline. IF, ID, OF, EX, MA, WB, 6 stages with 3 nanosecond clock. This is the code given, total 6 instructions given. All instructions are spending 1 cycle on all stages, but load taking 3 cycles on MA, ADD and sub taking 2 cycles on EX. Okay, amount of time saved to execute the code with operand forwarding over without operand forwarding technique. With operand forwarding, without operand forwarding technique. Okay. So first we need to prepare the table according to the given data IF, ID, OF, EX, MA, WB. Okay. Instructions I1, I2, I3, I4, I5, I6. 6 instructions given. All stages, all instructions are spending one cycle on all stages like this. Present. Okay. But load instruction spending 3 cycles on MA stage. I1 is load, 3 cycles. Then I4 is load, 3 cycles. Okay. And remaining one cycle. Next, ADD sub taking 2 cycles on EX. ADD. Second instruction is ADD, 2 cycles. Third instruction is all sub, 2 cycle. Fifth instruction is ADD, 2 cycles. Okay, and remaining one cycle like this. Okay, so based on the given question data, we formulated the table. Now apply the verification, dependency verification. Now I2, I1, see this, there is a dependency, input register, output register matching. When input register, output register matching, dependency present. I2 dependent on I1. Next, I3 input, I2 output, both are matching. Yes. So there is a dependency between I3 and I2. Okay. Then I5 and I4. I4 and I3, there is no dependency. I5 and I4, yes, there is a dependency. I5, I4, there is a dependency. Then I6, I5, yes, there is a dependency. Like this. So we identified the dependency among the instructions based on the given information. Now we need to calculate the execution time of a program with operand forwarding and also execution time of a program without operand forwarding. Then compare the both the times, report the value. Okay. So all of you please solve this question. I am also going to solve the question. Okay. With optimistic manner, you please solve it. No need to draw the diagram. No need to draw the diagram. Okay. Without space-time diagram, solve it. Right. In this, Optimistic method without drawing the space-time diagram, how we are going to solve the question, that is with operand forwarding, without operand forwarding. First, with operand forwarding. Okay, number of instructions given in the question is 6. 6 instructions total given, 6 inputs. Okay, right. I1 is always independent, there is no stall. So stalls are present due to the dependency. Now check this. Instruction 2 dependent on instruction 1. So here dependency detected in ID stage, but operand fetch takes place in OF stage. So as I explained earlier, data accessing takes place in which stage? That is most important in the operand forwarding technique. Okay, so in the RISC pipeline, operand fetching takes place in ID stage only, but it is a hypothetical question. Here data accessing takes place in the separate stage. So here operand fetch, here data accessing takes place. So this data accessing overlapping with EX stage. But EX stage buffer does not contain the data. This contain the effective address maybe, because of I1 is the load instruction. Load instruction output is available in the MA buffer here. Okay, this is the data. We want this data, not this one. So OF taking one cycle, EX taking one cycle overlapping. But we get the data after these 3 cycles. Therefore, here 3 stalls present. 3 stalls. Clear? Next, I3. Dependency detected in ID stage. Operand fetch takes place in OF stage. So OF stage overlapping with EX stage. I2 is the addition instruction. Therefore, EX buffer contain the data. Okay, one cycle overlapping, extra 1 stall present here. Next, I4. Dependency detected in ID stage. Operand fetching takes place in OF stage. OF stage overlapping with EX stage. But when you see the OF stage, okay, there is no dependency between I4 and I3. There is no dependency. Still it is waiting because of the stage. So this is the structural dependency. It is waiting for stage, not for data. I4 is not dependent, still waiting. Okay, that is 1 stall. This 1 stall is called as the structural hazard. This is the structural hazard. Okay, next come to the I5. Dependency detected. Operand fetching takes place here. Operand fetching takes place here. But this operand fetching overlapping with EX. Here EX buffer does not contain the data that contain effective address, because of I4 is a load instruction. Okay, then where the data present? Data present in the MA buffer. This is the data. Correct? So one cycle overlapping, extra cycles are 3. So 3 stalls present. Fine. Next, I6. Dependency detected in ID. Operand fetch takes place in OF, overlapping with EX. So EX stage contain data, because this is not a load instruction. So one cycle overlapping, extra 1 stall present. Okay, then last instruction, all stages are taking one cycle only. So there is no further extra cycles in the last instruction. Clear? So number of inputs are 6 inputs plus stalls. Okay, 3 plus 1, 4, 5, 8, 9. 9 stalls present. Correct? So n is equal to 15. 15 is a finite value. When n is finite, use the formula execution time equal to k plus n minus 1 into TP, cycle time. So 6 number of stages are 6 stages, correct? Then 15 minus 1 into 3 nanosecond. Clock cycle time 3 nanosecond, given or not? Here already cycle time given 3 nanosecond. So compute the value. $60 nanoseconds, correct? All of you got the answer, 60 nanoseconds. This is the execution time without operand forwarding. Now calculate the execution time with operand forwarding. Sorry, this is with operand forwarding. Now calculate the value without operand forwarding. With operand forwarding, without operand forwarding, okay? Right. In without operand forwarding, number of inputs are same. I1, I2, I3, I4, I5, I6. Number of inputs are same. I1 is independent. There is no problem. Then I2 is dependent, correct? I2. When I2 is dependent, stalls are present without operand forwarding. Without operand forwarding means after completion of I1 in the next cycle you may get the data. So here data available. So one cycle overlapping, 1 overlapping, extra 3, 1 and 1. So 3 plus 1 4, 4 plus 1 5. So here 5 stalls present. Next, come to the I3. I3 overlapping here, OF overlapping with EX. Got the point? So without operand forwarding means after completion we are getting the data. Here you are getting the data. So one cycle overlapping. Okay, extra cycles. Here it is 1 plus 1 2 plus 1 3 plus 1 4. So here 4 stalls present. Then I4. I4 is not data dependent. This is dependent on stage. So one cycle overlapping. So extra cycle is only 1. This is one stall. This one stall is a structural stall. This is a structural stall. So that it is not waiting for data. Then I5, data dependency. Okay. So here after completion you may get the data. One cycle overlapping. So 3 plus 1 4, 4 plus 1 5. 5 stalls. Okay, next I6. Data dependency. Okay, detected already. Then one cycle overlapping. But it is getting the data after completion. So that one cycle overlapping, extra one cycle 1 plus 1 2, 2 plus 1 3, 3 plus 1 4. 4 stalls. Okay. Now see the last instruction. Last instruction spending one cycle on all stages. Therefore, there is no further extra cycles in the last instruction. Okay, students. So total number of inputs are 6 inputs plus stalls are 5 plus 4 9, 10, 10 plus 9, 19. 19 stalls present. Okay, so n is equal to 25. 25 is the finite value. Therefore, execution time equal to k plus n minus 1 into Tp. Substitute the values. K value 6 plus 25 minus 1 into 3 nanoseconds. Do the calculation. 90 nanoseconds, correct? Now how much time is saved? So here time save equal to time save equal to 90 minus 60, that is 30 nanoseconds time is saved. Is it okay? This is the operand forwarding technique. And without operand forwarding technique, I solved the question without drawing the space-time diagram. Students, I solved the question without drawing the space-time diagram. No space-time diagram here. Okay, this is the answer. Logically, we calculated the answer. If you have any doubt, okay, draw the space-time diagram, cross-examine solution. So compulsory, your answer is matching. Is it clear? Please respond in the chat. Yeah, Sayan Kumar, you are asking why number of stalls are same? Because I4 is independent, right? This is I4. This I4 is not data dependent. I4 is not a data dependent. I4 is not a data dependent. Then why I4 is waiting? I4 is waiting for stage. I4 is waiting for stage. Okay, so that's what. See this? Here one cycle overlapping with one cycle. ये देखो, this is one cycle. Here two cycles. One cycle overlapping. Then how many more cycles it is waiting for stage? Only one. So that's what. This is common. This is structural hazard. Structural hazard, not a data hazard. That's what this is same. Okay. Sayan Kumar, it's correct na? 30 nanoseconds saved. DGS correct. Shambhav Jain, right answer. Pratik Sagar, I4 is independent. Yes. Okay, Vikas. Because this is the computer gate examination related concept. That's what the concept may be out of context according to your electrical background, right? Okay, because you said your background is electrical. This is the gate computer science related concept. That's what maybe this concept is out of context according to your electrical brain. Fine. Okay, students. So as of now, I covered the operand forwarding and without operand forwarding questions. Okay, I executed these two questions logically without drawing the space-time diagram. Okay, if you have any doubt, you please draw the space-time diagram manually and verify the solution. Compulsory space-time diagram solution and this solution both are matching. Pratik Sagar, okay? Alright. Fine. This is the next question. All of you see this question. Pratik Sagar, you said I2 is not dependent on I1. When I2 is not dependent on I1, there is no structural dependency, but there is a stall, sir. Yeah, I'm moving back to this. Yeah. Pratik Sagar, you asked the question. Nice question what you asked. Right? That question is I2 is not dependent on I1. Then what happened, sir? Yes. When I2 is not dependent on I1, coming back. Pratik Sagar, I am going to clarify your doubt. Okay, you just concentrate. You said, sir, I2 is not dependent on I1. What happens? Yes, I2 not dependent. So OF is overlapping with EX. One cycle overlapping. There is no stall. But here, see this 2 and 3. This is overlapping, no? In this order. When these are overlapping, this is taking one extra cycle, right? So this I2 EX overlapping with I1 MA. So here this will be waiting for 1. 2 cycle overlapping. Here one extra stall is present. Okay, Pratik Sagar, I hope you understand that. Okay, OF EX overlapping, there is no dependency. Okay, so one cycle overlapping, there is no stall. But EX and MA overlapping. But EX taking 2 cycles, MA taking 3 cycles, 2 cycles overlapping, extra one stall is created. Okay, Pratik Sagar, I hope you understand, right? Very good. So that's what, read the questions with careful attention. You may get the new ideas. Very nice, Pratik. Maintain the same confidence, okay? Good. Okay, your thinking level, okay, your analytical power increased, Pratik, what I observed. Very good. Maintain same energy, okay, till you reach your goal. Fine. See this question. Consider 5-stage pipeline with a cycle time of 2 nanoseconds, which allow all instruction except branch instructions. Target address is available at the end of 4th stage. Okay, ALU instructions penalty 2 cycles. No penalty is associated with the data transfer operations. Data transfer instructions, there is no penalty. Program contain 40% branch instructions, 35% ALU instructions, 25% data transfer instructions. Among the branch instructions, 60% are rearranged by the compiler. Okay, because delayed branch concept, they said. Average instruction execution time of the pipeline is. Question is expecting average instruction execution time. Students, please solve the question, give the right answer. Okay. My dear students, previously I explained the data dependency concept question, operand forwarding without operand forwarding. Many students are having doubts in that question, maybe, okay, due to lack of attention or anything. Okay, maybe you are not a MedEasy student, you may have so many doubts. Okay, after watching this session, I hope your all doubts are automatically eliminated. Okay, still you have any doubt, you just draw the space-time diagram, okay, and compare your diagram analysis with our optimistic logic. Space-time diagram taking more time and this optimistic analysis taking less time, but output will be same. What is the answer? Pratik, रजत भारती आंसर क्या? Yeah, DGS, you given the answer. Very good. Yes, some students are already given the answer. Thank you so much. So in this question, what they said, in the pipeline, all instructions are overlap except branch instructions. So here, branch penalty depends on the availability of target address. So that is fourth stage minus 1. This is equal to 3 stalls. What is the formula for branch penalty? At what stage target address is available, at what stage target address available, minus 1. This is the formula for the branch penalty. So that target address fourth stage में मिल गया. So that 4 minus 1 equal to 3 stalls. ALU instructions penalty separately they given. ALU instructions penalty. This we cannot able to estimate. That is mentioned in the question. That is 2 cycles, 2 stalls. Alright. There is no penalty associated with the data transfer operations. Good. Now report the further information. There is a program. See this. There is a program. Okay. In this program, what we have? 40% branch instructions. Branch. Okay. Then 35% ALU. These are the ALU instructions. And 25% data transfer instructions. Like this program contain different instructions. That is mentioned clearly. Okay. So data transfer instructions, there is no penalty, 0 stalls. ALU instructions, there is a penalty, 2 stalls, 2 cycles penalty. In 40% branch instructions, see this. Okay, among the branch instruction, 60% are rearranged by the compiler. You know that. Here 60% of branch instructions are rearranged. When rearrangement happened, there is no stalls. You know that. When compiler rearranges the branch instruction, stall is not present. Okay. Then 40% are not rearranged. Not rearranged means NOP inserted. NOP inserted. How many NOPs inserted? 3. Because branch penalty already identified 3 stalls. 3 NOPs inserted. Okay, students? Very good. So now calculate the average number of stalls per instruction. First, calculate number of stalls per instruction. Okay, that is equal to how many? 0.4 into 3 plus 0.35 into 2. That's it. Okay, report the value. .48 plus 0.7. .18. Okay. So now, what is the average instruction execution time? Formula is average instruction execution time is equal to 1 plus number of stalls per instruction into cycle time. This is the formula. Okay, so this is 1 plus 1.18 into what is the cycle time? Cycle time already given in the question, 2 nanoseconds into 2 nanoseconds. So report the value. .36. This is the average instruction execution time. Okay, so in this question, branch penalty we need to decide based on the availability of target address. ALU penalty already given in the question. Okay, data transfer penalty not given, that means 0. Also they mentioned rearrangement done by compiler. When compiler rearrange the instruction, there is no stall present. If rearrangement is not possible, stalls are present. Okay, by using this logic we solve the question. Answer is 4.36 nanosecond. Let me see how many of you given in right answer in the chart section. Sayan, Shambhav, DGS, yeah, you are given right answer. Thank you so much. Okay, like this solve the pipeline questions. Okay, all right, now I am move on to the memory organization, right? Let us see the memory organization concept. Okay, so in the memory organization mainly we are going to focus on cache memory design. Okay, so before that we try to understand the simultaneous access memory design and hierarchical access memory design concept. Already we know the simultaneous and hierarchical structures. So based on that we are going to identify the formulas. So major formulas used in the memory organization is, first thing, performance is inversely proportionate to access time. Performance of the memory inversely proportionate to access time. Memory functionality storage. Okay, quick accessing, more performance. That means accessing time is low, performance is high. Right? Now, here when we have a simultaneous access memory organization, simultaneous access memory organization, there we have a formula, that is the T average is equal to, okay, H1 into T1 plus 1 minus H1 into H2 into T2 plus 1 minus H1 into 1 minus H2 into, okay, H3 into T3 and so on. This is the formula. This is the simultaneous access. Then hierarchical access. Hierarchical access memory organization. Hierarchical access memory organization formula is T average equal to H1 into T1 plus 1 minus H1 into H2 into T2 plus T1. So higher level to lower level data transmission takes place. Similarly, 1 minus H1 into 1 minus H2 into H3 into, okay, T3 plus T2 plus T1, okay, and so on. Okay, so this is the formula, average memory access time formula. And sometimes some questions are having the terminology mispenalty. So T2 plus T1 itself directly name it as a mispenalty. Okay, when there is a miss in the level 1, miss penalty of level 1 is some value given. So that miss penalty means T2 plus T1 value together name as the miss penalty. Okay, all right. Next one. If you see the cache memory, if you see the cache memory design, in the cache memory we have a different terminologies. That means cache memory will be organized into lines. Okay, so number of lines depends on the cache capacity and block size. Cache memory size divided by block size. Okay, by using this you can measure the number of lines. After that, in the cache memory we have the different mapping techniques. Okay, so here mapping is direct mapping. In the direct mapping, mapping function is k mod n equal to I. This is the mapping function used. After that, address format is tag, line offset and word offset. This is the address format used. Then associative mapping. In the associative mapping, okay, there is no particular function. This is counter logic. Any main memory block can be mapped into any cache memory line. So address format is tag and word offset. That's it. There is no address present. Line offset not present in associative cache. Then set associative mapping. In the set associative mapping technique, what we have is number of sets S equal to n by p by. First calculate the number of sets. After that, report the mapping with mod function k mod S equal to y. This is the mapping function. Okay. Then address format is tag, set offset and word offset. This is the address format. Clear now? Very good. In the three types of mapping, there is no FIFO and LRU techniques. No need of any replacement techniques in the direct mapping. In the direct mapping, there is no need of explicit replacement techniques. Mod function itself indicates the replacement. Whereas in the associative mapping, FIFO and LRU techniques are used, and set associative mapping, FIFO and LRU techniques are used to replace the data when set is full. Here replace the data when cache is full. Like that, mapping techniques are used in the cache memory design. Okay. At the same time, in the cache memory, we have a techniques of updation. Okay. When CPU performing the updation, if only the cache memory is updated, main memory is not updated, there may be a possibility of coherence. Okay. To handle that coherence, we have the techniques, write through technique and write back technique. Write through means simultaneous updation in both of the memories. There is no coherence. Write back means only cache memory is updated, the corresponding line update bit is set. Okay, so that is called as the dirty case. Okay, so before replacement, dirty blocks are copied back to main memory. Later replace the cache blocks. So even coherence is present, data loss is not present in the write back cache. Like this we can manage the updations. Okay. Then multi-level cache design is the further enhancement. When we have the multi-level cache, performance will be improved. That means when there is a miss in the first level cache, instead of going directly to main memory, we are checking the second level of the cache for the availability of the data. So like this, system performance will be improved by introducing the multi-level caches. Okay, so you know all the respective formulas which are used in the multi-level cache design and write through and write back protocol, right? So apply that logic to solve the questions. Okay, generalized formulas already known to you, so directly we are using them in the analysis. At the same time, when you see the cache memory, there are three types of misses present. One is compulsory miss, second is capacity miss, third is conflict miss. Compulsory miss means the very first time referenced block in the program is not in the cache. Okay, capacity miss means cache block is replaced from the cache memory when cache is full. So that replaced block we want in the future, that is not available in the cache. That is the capacity miss. Capacity miss is occurred when cache is full. Conflict miss, when too many blocks mapped into same cache line, then cache blocks are swapped out. That swapped out cache block, if you want in future, that is not available in cache. That is called as the conflict miss. Like that, three types of misses present in the cache memory. Clear? That is the refreshment of the cache topic. At the same time, after completion of the cache memory, we have a secondary memory design. Secondary memory. With respect to the secondary memory concept, we are taking the help of the hard disk. Okay, hard disk is acting as a primary secondary memory in the personal computer. Okay, so nowadays there are so many latest technologies available, but according to the syllabus we are going to discuss the hard disk structure. Okay, so as far as the hard disk design is concerned, there are the different times are associated to access the data from hard disk. Okay, so the direct formula used to calculate the average access time of a data from the hard disk is average seek time plus average rotational latency plus transfer time plus overhead. So this is the direct formula used to calculate the average memory access time of a hard disk. Okay, average seek time plus average rotational latency plus transfer time plus overhead. All right, so based on this information, we are going to see some set of the questions. Okay, for your practice. See this question and give the answer. Okay, in this question, what is mentioned here? Consider cache memory with a hit ratio of 80%, access time of 40 nanoseconds. Access time of a main memory is 5 times of a cache memory access time. What is the average memory access time? Okay, so whenever question contain cache memory, by default we are using hierarchical formula, because cache memory by default principle is locality of reference. Okay, so now T average is equal to HC into TC plus 1 minus HC into Tm plus Tc. Is it okay? This is the formula, correct? Now HC 0.8, TC 40 plus 1 minus HC into Tm, 5 times of cache memory, that is cache memory access time is 40, main memory access time is 5 into 40, that is 200 nanoseconds plus 40, Tm plus Tc. Okay, report the answer. $32 plus $48. that is straight away 80 nanoseconds. Okay students, 80 nanosecond is the answer. According to your option, C is matching. So answer is C. It's a direct straightforward question. Okay, so everyone can easily answer this question. Fine. Okay, next question is this. Students, this is the question. Read it. Yeah, Rajat Bharti, Pratik Sagar, you all are given the right answer. Very nice. My dear students, you please don't think that Sir is not explain the concepts more. Okay, no need to explain the concepts here. Okay, this is just the session to recap the information. That's it. That's what I am not going into the detailed analysis of each concept. I just make a review of the basic fundamental formulas, and later I am explaining set of questions. That's it. To recap the total information from your brain. This is the question. Now see this. Consider cache memory. There is a cache memory with access time of 50 nanoseconds. Hit ratio of 70%. Miss penalty of cache is 300 nanosecond. Average memory access time is. This is the question. In this question, there is no main memory access time given. Directly they mentioned the term miss penalty. So we are using the formula like this. T average is equal to Sagar, Pratik Sagar. T average equal to TC, HC into TC. Hit in cache, access from cache. 1 minus HC, miss in cache. When there is a miss in cache, directly penalty will be associated. Whenever question contain the miss penalty for term, directly you can use this formula. So no need to use Tm plus Tc. In the question, main memory access time is not given. Then how can we use Tm? Directly you can take miss penalty value. Okay. So this is 0.7 hit ratio into access time 50 plus 1 minus 0.7 miss penalty 300 nanoseconds. That's it. $35 plus 90. This is equal to 125 nanoseconds. Okay. According to the options, when we see the options, B is matching. Answer is B. So according to the question terminology, you may use the formulas. Okay, all right. Sagar Kumar, thank you so much. Jiban Krishna, Rajat Bharati. So whoever watching the live session and whoever going to watch the live session later, you please concentrate on that pipeline questions once again. Whichever the questions I explained in the live session, okay, with operand forwarding, without operand forwarding, they are some special questions. Okay, usually I explained already the questions with 4-stage pipeline or risk pipeline. But in this session, I took the hypothetical pipelines, okay, where operand fetch takes place in the separate stage. Okay, in our regular class notes, always operand fetch included in the ID stage. That's what ID stage overlapping with EX stage. Like that we analyzed the classroom questions. But hypothetical questions are different. That is the reason all of you please focus on those operand forwarding, without operand forwarding questions to get the more information logically. Okay, accepted my voice? Yes. Now take another question. See this. Please go through this. What is mentioned? Consider direct mapped cache of 2 KB organized into a 512 byte blocks. Okay. Following main memory blocks are referred by the CPU during program execution. Okay, these are the sequence of the blocks. Fine. Which of the following statements are true? Bus. You need to identify the true statements. Do it quickly. Yeah, miss penalty definition is what? Actually, DGS, miss penalty definition is amount of the time required to access the data when there is a miss in respective level. That's it. Okay, how much time CPU taking to access the data from the memory when there is a miss in level 1. That is the miss penalty of level 1. Miss penalty of level 2. How much time CPU taking to access the data from memory when there is a miss in level 2. That is the miss penalty of level 2. Okay, right. That is the definition, miss penalty. DGS, is it clear? Please respond. Very good. Thank you, DGS. And one more point I want to make clear. Okay, many students are not going to touch computer organization and architecture subject. Many students, because a lot of fear is there in the student mind about the computer organization and architecture questions. That's what they are throwing this subject into dustbin, at some side. Okay, but that is not the good sign actually. Computer organization is not that much complex subject. Okay, static subject. Structure is static, concepts are static, terminology is static, questions are also static. Maybe some numerical values are changed in the question, some logic will be changed here and there. Okay, when you know the concepts of computer organization, compulsory you are in a position to answer all the questions of COA. Okay, so when many students are throwing this subject into dustbin, few of you are hold this subject in your hand. Compulsory you are solving COA questions in the paper. Many are not solving, you are solving. Okay, then your rank is improved. So this subject is rank improvement subject. So don't overlook COA subject. Okay, so you please take this subject into your heart. Then this subject gives more happiness in your success. Okay, very nice. Then what is the answer? Here given information is direct mapping. Next, cache memory size is 2 KB. Next, block size is 512 bytes. Okay, so number of lines equal to cache memory size by block size. That is 2 power 11 by 2 power 9. That become 2 power 2. So 4 lines are present. So these are the sequence of blocks required. Fine. Then calculate the value. Here total 4 lines. 0, 1, 2, 3. Mapping function is what? Mod function. K mod n equal to I. Then apply the logic, solve it. First 3 is miss. When it is miss, 3 mod 4. Okay, line 3. mapped. Next 8 is miss. So 8 mod 4 0 mapping here. Then 7 is miss. 7 mod 4. Please all of you try to solve this because this is also important question. So 3 is replaced. 2 is miss. 2 mod 4. Mod operation invokes the division, returns the remainder. So 2. Okay. Then 1 miss. 1 mod 4. 1. So here. Right. Next 4. 4 is miss. 4 mod 4 0. So 8 is replaced by 4. Then 3 miss. 3 mod 4, that is 3. So 7 is replaced by 3. 5 miss. 5 mod 4 1. So 1 is replaced by 5. Next 4 hit. 4 hit. 3 hit. 4 hit, 3 hit. Then 7 miss. When 7 is miss, 7 mod 4 is equal to 3. So 3 is replaced by 7. Done. Then 4. 4 is hit. Then 8. 8 is miss. So 8 miss means 8 mod 4. That is equal to 0. So now 4 is replaced by 8. That's it. This is the way to access the data. Now answer the question. First, which of number of compulsory misses are 7? What is compulsory miss? What is compulsory miss? Compulsory miss means number of unique block references in the program sequence if and only if cache is empty. So in this question, cache status not given. When cache status not given, default cache status is empty. Default cache status is empty. That's it. When cache status is not given, assume that cache is initially empty. So number of compulsory misses is equal to number of unique block references in the sequence if and only if cache is empty. Now count unique references. 1, 2, 3, 4, 5, 6, okay, 7, and remaining all are repeated only now. So number of unique blocks in this sequence equal to 7. So number of unique block references is equal to the number of compulsory misses if and only if cache is empty. So that first statement is true. They are asking true statement. Fine. Now come to second statement. What second? Hit ratio of the program is 0.23. Now calculate hit ratio. Number of hits 1, 2, 3. Only 3 hits. 3 hits upon number of hits. 3 hits upon how many references? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 3 upon 13. What is the answer? 3 upon 13 is equal to 0.23. Okay, right. Now this is also true. Second statement is also true. Next, number of conflict misses are 3. What is conflict miss? Conflict miss means whichever the block is replaced in the line, if that block is required in future, that is not available in the cache. That is the conflict miss. Now see this. So here 8 is what? Compulsory miss. 4 is compulsory miss. Now here 8 is replaced. Na? So replace the 8 I want here. So this is called as the conflict miss. This is conflict miss. Okay. Next, 1 is the compulsory miss. Then 5 is also compulsory miss. Okay. If 1 is required in future, that become a conflict miss. Okay. Alright. Come to this. 3 is a compulsory miss. 3 is a compulsory miss. Okay. 7 is a compulsory miss. Okay. Now this 3 conflict miss. 3 replaced, I want this. Now 7 conflict miss. This is a conflict miss, and where 3? Yeah, 3 is a conflict miss. Correct na? So this is conflict miss, this is conflict miss, this is conflict miss. So total 3 conflict misses present. Yes, this is also true. Number of conflict misses. Got the point? Conflict miss means what? The replaced block in the cache required in the future. When replaced block is required in future, that is not available in cache. So that miss is a conflict miss. Fine. Next, block 2 is not replaced by any other block in the cache. Yes, this block 2 is remains present. So this is also true. Then right answer is all the options are true. Okay students, I hope you understand this analysis. In this question, correct answer is A, B, C, D. How many of you given the right answer? Please let me see in the chart section. And remaining students, you just watch the analysis, what I explained. Yeah, Shambhav Jain. Shambhav Jain, you asked the question, sir, how to remove the compulsory misses. Dear students, okay, Shambhav Jain, not only you and remaining students also, we cannot remove any miss. We cannot remove, like a stalls, in the pipeline stalls, can you remove all stalls? No, we cannot remove all stalls. We are minimizing the stalls. Similarly, in the cache memory, compulsory misses can be minimized by increasing the block size. When block size increases, number of unique blocks are decreases. Number of unique blocks decreased means number of compulsory misses decreased. Got the point? Yes. Compulsory misses can be minimized by increasing block size. Capacity misses can be minimized by increased cache capacity. Conflict misses can be minimized by double the associativity of a cache. Like this, minimizing, not removing. Shambhav Jain, is it okay? Very good. Very good, very good. Dear students, thank you so much. You all are given right answers. Very nice. Now I am going to display another question which is related to cache memory. Let me see how many of you are giving right answers. Okay, one point. Dear students, actually nowadays questions are become very lengthy because of multiple selection question. Okay, to answer question, okay, you should know all the surrounding concepts. When you know all surrounding concepts, then only you are eligible to answer the questions. Okay, so be careful. Just watch this and answer the question. All of you, do it fast. I am also reading the question along with you. Just see the question. Consider 8-way set associative cache. They given 8-way set associative cache of 256 KB organized into 64-byte blocks. Very good. CPU generates 24-bit physical address to access the data. Okay. In the cache controller, each tag is comprising of one valid bit and one update bit. Which of the following statements are true? So we need to identify the true statements. Okay, according to the given data, you need to decide whichever the following statements are true statements. Do it. Pratik, what you said? Increasing number of blocks can minimizing. Arey, block size increase. Pratik Sagar. When block size increases, number of blocks in the cache decreases. And also number of blocks in the main memory decreases. You know? Suppose block size is 2 byte. More blocks are in main memory, more lines are in cache memory, correct? When block size increases, then what will happen? Number of main memory blocks are decreased or not? At the same time, there is an effect in the cache memory lines also. But when the CPU refer the data, okay, CPU referring the main memory blocks only. So when main memory blocks are, number of blocks are decreased, unique references are also decreased in the program. That's what compulsory misses are minimized. Okay, Pratik? Do you understand? Please respond. Motivational shots. Very good, very good. Right. Now see. Here what is mentioned? 8-way set associative cache given. 8-way. Okay, cache capacity 256 KB. Okay, then block size. Block size is equal to 64 byte. Then obviously number of lines n is equal to, okay, 256k by 64. 2 power 18 by 2 power 6. This is 2 power 12. 2 power 12. Okay, right. Number of sets s equal to n by p way. N by p way. So n 2 power 12. P is 8. Given 8. So this become how much? 2 power 12 by 2 power 3. So this is 2 power 9. Number of sets are 2 power 9. Okay, all right. Now address format. First let us see all things, all possible things, surrounding elements. Okay, right. Now automatically if you see the address format, main memory address 24-bit address given. Now tag, set offset, word offset. Word offset is 6-bit because block size is 64 byte. Then set offset is 9-bit. Okay, and remaining bits are the remaining bits are the tag space in the line. In each line of a set we have a 9-bit tag space. Is it okay? Please verify. Verified? Very good. Now come to this. First statement, what they given? Each line of a cache set contain. Each line of a cache set. How many lines are present in the cache set? 8 way. So 8 lines are in each set. Okay, contain 9-bit tag space. Yes, this is true. Already we estimated there. Next, 44k bit tag directory. This is not tag direct. This is the tag directory. Tag directory. This is a printing mistake. 44k bit tag directory is present in the cache controller. Yes. Then what is this meaning? How to calculate tag directory? So tag directory size equal to, okay, n into tag space in the line. Okay, correct. So some students, they may use in place of n s into p, no problem. So n is equal to 2 power 12 into tag space. What is the tag space? 9 bit plus, apart from 9 bit, one valid bit and one update bit. One valid bit, one update bit present given in the question. So this is equal to 2 power 12 into 11 bit. This is equal to 44 kilobit. Yes, this is also matching. So second statement is also true. True statement. Is it okay? Now third statement, C. FE2484. Now see this, FE2484. This is the hexadecimal address given. Hexadecimal address given here. Okay, F1111, E1110, 20010, 4010004. Next 8 1000 and 40100. Okay, now interpret this in the above format. Right, 6 bits, 1 2 3 4 5 6. 6 bits are used for the word offset. Next 9 bits, 1 2 3 4 5 6 7 8 9. 9 bits are used for the set offset and remaining bits are the tag space. Okay, so I want to find out the set number. See this, 1 2 4 8 16 32 64 128. Okay, this is how much? 146 base 10. 146 base 10. That means the corresponding addressed main memory data present in 146 set. Okay, so according to this question, see this, a statement be true hai. See, this is also true. Okay, right. In each set of a cache, 512 different main memory blocks are possible to map. In each set of a cache, 512 different main memory blocks are possible to map. This statement is also true. How you can say true? Reason is, see this, in each line, dekho, in each set, how many bits of tag space is there? 9 bit. Okay, set offset associated with 9 bit tag space. 9 bit tag space means what? 512 2 power 9 combinations possible. Total 2 power 9 combinations possible. 2 power 9 means what? 512 main memory blocks are possible to map. 512 main memory blocks are possible to come in the same set. But not at the same time. Okay, because we have a 8-way set associative, so that at a time 8 main memory blocks you can accommodate. After that, replacement will be happened. If this is the case, how many possible blocks are supposed to come in the same set? 2 power 9, because 9 bit tag space, 2 power 9 combinations are present. So this is also true. Therefore, in this question, right answer is, what are the statements? True. So all statements are true. A, B, C, D. Let me see how many of you given right answer in the chart room, in the chart section. Yeah, Sagar Kumar, DGS, you all are given right answer. Amit, Jiban Krishna. Yeah, some students are confused with last statement. Some students, but don't confuse, dear, because in the classroom, regular classroom also, I explained that. Don't confuse. Is it clear? All right. This is in each set 512 different blocks, because tag space is 9 bit na. 9 bit tag space means 2 power 9 combinations are there. So total 512 blocks are possible to come in the same set, but not at the same time. Okay, so at the same time only one block is coming. Like that, set can able to accommodate 8 blocks. After 8 blocks, replacement started. Okay, I saw if you replace the data, how many possible blocks are coming? 512 blocks are coming. That's it. Okay, students, right. Very good. So in the GTQ, gate through question session, I explained some important question of cache memory. You just go through the GTQ. There also I given very good question. Okay, I explained very good question from the cache memory design. Okay, so you please go through the gate through question session, GTQ question, that is available in the YouTube from the MadeEasy channel. So go through that. Okay, I already forwarded that link to the respective groups. So watch that GTQ session also. In that session, I explained some strange questions and important questions from the pipeline as well as the cache memory along with other concepts. So don't miss that session. Okay, that is already available in the YouTube. I forwarded the link. So there you have some other set of the questions, either from cache memory or from pipeline or from any other topic. Okay, to get more information, watch that. Okay, take the question, practice, take the question, practice. It gives the good analytical improvement. Very nice. Fine. So let me take one more thing related to DMA concept. Okay, as of now we covered all these. So next thing is the IO organization. Okay, this is a small topic actually in our syllabus, correct? IO organization. IO devices are electromagnetic components. CPU is a electronic component. Between these two components, if you do the data transmission, there is a possibility of synchronization. Okay, data synchronization required. For that purpose, we are introducing the IO interface chip to minimize the speed gap. Because of IO interface chip, CPU informed to the IO interface chip about IO operation. Okay, later CPU busy with other program. IO interface chip is responsible for IO operation. Once the IO data is ready, IO device send the data to interface buffer. Interface buffer sending the data to CPU with proper interrupting signals. Okay, so in this way, speed gap is minimized between CPU and IO devices. That means CPU will be accessing the IO devices data from the interface buffer, not directly from the IO. That is the way to minimize the speed gap between CPU and IO. Okay, so in that IO we have a 3 modes of data transmission: programmed IO, interrupt IO, DMA. In the programmed IO operations are programmed in the CPU only, so that CPU will be waiting until IO operation is completed. Okay, so processor utilization is very poor. Then interrupt driven IO. In that interrupt driven IO operations are controlled based on the interrupt signals. Therefore CPU time utilized properly. Okay, right. DMA. In the DMA concept, DMA is separate interface chip which is responsible to transfer the data from IO to main memory. Okay, without involvement of a CPU. Okay, without involvement of CPU, to transfer the data, DMA is supposed to get the system bus from the CPU. To get the system bus from the CPU, DMA utilizes the hold and HLDA signal, hold acknowledgement signal. Okay, in that DMA we have different modes: burst mode, cycle stealing mode and interleaving mode. In the burst mode, after data preparation, take the control of the system bus, transferring the data separately, so one by one. In the cycle stealing mode, preparation and transmission both are executed in parallel by using overlapping order. That is the reason when we are calculating the percentage of CPU time consumed in the burst mode, y upon x plus y into 100. Whereas in the cycle stealing mode, percentage of CPU time consumed is y upon x into 100, because in the cycle stealing mode, overlapping takes place between the preparation time and transmission time. In the burst mode, there is no overlapping, one by one. Interleaving mode means when CPU busy with the local bus operations, DMA utilizing the system bus to transfer the data word by word. Already you know this concept. Okay, let me explain one question which is related to DMA. Right? Now take this question. Usually this kind of question is possible in the paper. Just read the question and try to solve it. Okay, so here in this question, what they given? Consider 4 Mbps IO device connected to 64-bit CPU using DMA interface. 64 words data transferred from IO to memory using DMA interface. Main memory machine cycle time is 0.5 microseconds. Percentage of CPU time consumed. Consumed matlab blocked in the DMA operation is. So here what you need to do? DMA modes are not given. Okay, when not given, default mode is burst mode. Here cycle stealing term is not given. That's what we are using the burst mode. Okay, right. First see the preparation time. Data preparation time. Data preparation time usually denoted with X. Denoted with X. Denoted with X. Okay. Data preparation time depends on the speed of a device. IO device only preparing the data. What is given? 4 MB data transmitted in 1 second. 4 MB data transmitted in 1 second. How much data you want to transmit? 64 words. 64 words data preparation takes how much time? 64 words. 64 words means 64 into, what is the word size? That is 64 bit. Clear? So 64 into 8 bytes. Is it okay? Right? This is equal to 512 bytes. Clear? So if you take the 512 bytes data preparation, how much time is required? That is equal to, calculate, 512, see this, 512 bytes upon 4 MB seconds. This is the X value. Okay, byte cancel. Right. 512 divided by 4, that is 128 microseconds. Is it okay? So 128 microseconds. Then what is the transmission time? Y is equal to transmission time, right? Transfer time is Y. So this transfer time depends on the machine cycle. So one machine cycle means one word accessing time, or one word reading time, or one word writing time is the machine cycle. So one machine cycle means one word accessing. Here how many words we need to transfer? 64 words. Requires 64 machine cycles. Okay, machine cycles. Is it okay? Right. Therefore here Y value is equal to 64 into every machine cycle taking 0.5 microseconds. This is equal to 32 microseconds. Is it clear? All right. So preparation time you know, and also transfer time we calculated. Now apply the formula. Percentage of time CPU blocked is equal to Y upon X plus Y into 100. That's it. So Y 32 upon 128 plus 32 into 100. Okay, do the calculations. What is that? 20%. Is it okay? Now when you see the options which is matching, that you need to select. Okay, percentage of CPU time consumed in the DMA operation is 20%. So here answer is B. B is matching. Is it clear, dear students? Like this you need to solve the DMA question. How many of you given right answer? Let me see. Yes, B. Shambhav Jain and Chakravarti Sayan given the right answer. Very nice. Very good, Pratik. So all my dear students, your all answers are matched. Okay, very good. Thank you so much, my dear students. You given the prompt response and also accurate outputs, right? And some student DGS, don't know who. DGS, you only asked the point about the write through and write back protocol. Actually, write through protocol means what? Simultaneous write operation takes place in both cache memory and main memory. When simultaneously we are performing the write operation, what will happen is coherence never present, inclusion always success. Lower level memory data always subset of a higher level memory data. Correct? So parallelly we are transferring the data means there is no need of the there is no compulsory of write allocate policy. So whichever the block is updating, directly you can update in the main memory. Correct? So write through protocol, simultaneous write operation takes place, so that there is no coherence at all, inclusion is always success. Write back protocol means compulsory cache memory will be updated. So there is a coherence present. When coherence present, data loss is associated. To handle data loss, In the write back cache design, one extra bit storage space is allocated in each line. So that extra bit is called as the dirty bit. Okay, that bit is set when the cache block is updated, otherwise reset. So before replacing the cache blocks, updated cache block is copy back to main memory. Later replace the cache memory data. So updated data will be safe. Like this, even coherence is present, data loss is not present in the write back cache design. So write through, write back, these two concepts used in the cache memory organization to handle the writing issues. That is the story. So this point I already explained in detail with the formulas in our regular running notes. Watch that. Right? So as of now, I explained all the questions and concepts as a just recap of your existed information. Okay, so you all are given the correct support with more accurate prompt answers. Okay, thank you students. So this is the actually end of our session. In this session we covered all the concepts recap along with the sample questions. I hope you enjoyed all the questions and all the concepts the entire session. Okay, all the best my dear students, and God bless you all. Finally, your hard work is matter. Okay, success always likes hard work. Okay, so if you are doing hard work, then success is yours. Thank you so much my dear students. Thank you all. Bye bye.